Hmm? Yeah, sure. That's it. It's on. Okay, perfect. Just get some water. Just one second. Come. Take some water. Just the glass. कप नहीं है पेपर कप नहीं पेपर कप ठीक है oh. I hope the Zoom is not on.
Okay, so welcome everybody to the next week. Hope you had a nice week. Okay, last week was nice. Okay, another week. So we'll start with our first set of first lectures. So it's going to be given by Arnab Pal from IMSC. So he is going to give lectures on stochastic resetting. Yeah. Okay, Arnab. Again, yeah, you can ask questions during the lectures, and okay, you have tutorials.
Okay, so good morning everyone. So, thanks Sanjeev and Abhishek for this kind invitation. This is my 5th time actually in the school, 4th being over there as an audience, as a student, and this is the thing, I'm here. And also, the school started when I was in 2nd year. And it's actually so pleasing to see that it's still going, big guns. And so I think I have a lot of fond memories from the school. And a big, applause to Sanjeev and Abhishek, for being persistent torchbearers for this school, which is going so well. Okay, so what I'm going to do is I'm going to give 5 sets of lectures on resetting. And it will be mostly theory, teaching you methods and stuff like that. And there will be a few examples through which I will try to motivate you how to use these methods, for different kind of setups. And then there will be one or two particular examples at the very end where I will sort of show you how resetting can be used in real life applications. Okay, so so let me just start. So this is the like a brief outline. So I suppose that you had some sort of a prerequisite needs needed, like for example, I hope that you know Brownian motion, diffusion equation and stuff like that. Well, still I sort of will go over them. It will be like a crash course, like half an hour stuff. And then I will come to resetting. And then I will show, teach you some sort of methods and some concept of something called steady state. And then I will teach you something called first passage properties. I will sort of so I will explain what I mean by first passage properties. Oh, till what you can see? Till here? Yeah, this is fine? Okay. Okay, and then some applications. Okay, so this is more or less like a brief outline of this sort of set of lectures, and of course I will toggle between things. Okay, so this word of reset or resetting, right, should not be very unfamiliar to you guys, because like every time you are stuck, like let's say you are doing a project or something and you hit a roadblock, and typically what you do is like, okay, let me just like go out of this project for some time, think about it, and so this resetting of your mind setup sort of helps you take a different path and attack the problem in somewhat different way, right? So and this what you I mean, as we have seen that these are not just qualitative anecdotes, but also like they can be used in a real practice. Okay. So we'll see like these applications as we move along. Okay. So the first part, like the first like half an hour, let's say, I'll just move this guy a bit. I cannot see the clock. Okay. Oh, this is fine. Okay, so the first half an hour or so, I will just sort of like recap this classic Brownian motion or diffusion, Fokker-Planck equation, etc. So let's get started. So first is like, imagine that you have a random walker, right? So it's a discrete time continuous space random walker. So let's say that the walker starts from 0 and like discrete steps. But it can jump anywhere, okay? So there is no sort of like stopping. So if I denote the position of the walker by x and at time and step n, so the evolution equation for this guy should be xn is equal to xn minus 1 plus xi n. Okay? So what is the xi n? So xi n is essentially the step length. Okay, as I said that it can take arbitrary jumps. Only thing is that it should come, it's a random quantity, so it should come from some distribution, right? So the distribution of this guy, let me just write it in this way, and in such a way that like it has two properties. One is the mean is 0, just for the sake of simplicity, and it should have a finite variance. Okay, so it should have a finite variance, meaning this is finite, and let's just call it sigma square. Okay, so if this is the like rule of the game, okay, so what I'm interested in is the position distribution of the walker after n steps, because after n steps, every time you do this experiment, the walker will be at different position. So this final step will be different. So you have to talk about distributions, right? Okay. So what I can do is I can just sort of like reiterate this process, right? So let's say that I was at time 0, I was at the origin, right? And then I kind of reiterate it. So x0 plus xi1. So this is just xi1. Similarly, if you just go along till here, so it will be summation over xi, right? So if this is the case, so what is the mean position of the walker after n steps? So you see that it's just sum over this, and also then it's average over this one, so it's 0, right? So this is 0, and so if xn square, if I want to calculate the the second moment, so or the standard deviation, the mean is 0 anyways. So what you can do is you can just do over two sums, right? So and then these sums essentially go over. So this is this sigma j. Yeah. So if you do this, right? So if you do this, both these sums essentially go from 1 to n, right? If you do this sum, what you will get is something like n sigma square. Okay. So the mean square displacement essentially goes as proportional to n, right? This is something all of you know very well. Okay. So the next step is usually like the reason why I'm doing it, because like we will be using some sort of the way we will solve the the propagator for this problem also will be useful for the case when I add the resetting. Okay, so if I do this sort of like background thing, so it will not be very difficult for us to sort of like move to that. Okay, so now what the usual idea is that this was sort of like a discrete time continuous space, right? And we are all familiar with the typical Brownian motion. So in the typical Brownian motion, we have both space and time continuous, right? So what we can do is we can just imagine that, okay, now let's say we have the continuous time, okay, and let me just write it in this way. So these are my steps n, right, and the interval is delta t, okay. So if I something like this, so and my aim is essentially to calculate x of t square, okay, in the continuous time limit, okay. So this is actually very simple. What you can do is you have n here, right? So you start from this. So this is the aim, right? So you start from xn square, and this n you replace by t by delta t and sigma square. Okay. This is just a simple. I mean, I just substitute this one over there. Okay. And now let me just rewrite this. So sigma squared by delta t times t. Okay. So now, as I said, that if you go to the continuous time limit, so I have to take delta t going to be 0, right? So if I have to take delta t going to be 0, right, and I know that the mean square displacement have to be finite, right? So this quantity itself should be finite, right, in the delta t going to 0 limit, right? And this is something which sort of we define this as a diffusion constant, okay? So this is like the diffusion constant. Just to give this a meaningful interpretation, and in such a way, so what we get is x square is basically 2d t, okay? And what is going to be the, like the continuous version of this evolution equation? So if I want to write the, the continuous time so for this, let's start from this one, right? So we have xn is equal to xn minus 1 plus xi n, right? And this is the, this is the discretization process, right? So what do? Is we take this guy over here, okay, and divide both sides by delta t. So this becomes and this is, let's denote this guy by something called a continuous random noise, okay. So this is a random noise whose statistical properties need to be evaluated using the properties of psi of n, correct? Clear? Okay. So if I do this, right, so let's try to calculate the statistical properties of this one, right? So this xi of t, if I take the average of this guy, right, so what should be this? So this also goes to the average of this one, right? And then this is 0, right? So this is 0. Very well. Okay. So now let's try to calculate this guy. Okay. Okay. So what is this guy? So this basically goes here, right? The square of the angular bracket over there, right? And xi n square angular bracket is something we know already, right? What was it? Sigma square. Okay, so sigma square by delta t square, right? And we can see that we have actually introduced this diffusion constant by sigma square by delta t, right? So sigma square by delta t is 2d, right? So sigma square by delta t is basically 2d divided by delta t. Okay. Okay. So what we see is that the statistical properties for this random noise, right, this continuous time random noise, actually has this property that when delta t is going to 0, it has the highest effect. And as if we look into two different time intervals, xi t1 and xi t2, there is no correlation. Okay, then it becomes 0. Okay, so a physicist way of like approaching this guy when delta t is going to be 0, right? So when you have delta t going to be 0, so we sort of like tell that, okay, we can interpret this as a delta function, as a Dirac delta function. Okay. So you see that this is some sort of, like there are quite a bit of abuse of notation here and there, but this is like sort of like a physicist way of understanding this. So if you go from this discrete time random walk to continuous time random walk, continuous time Brownian process, and you do this, like step by step, the all the steps essentially. So you see that you get a discrete, a continuous time evolution equation for the position, okay, where there is a noise which is appearing over here, which has some sort of like statistical properties, okay. So this way is it? Yeah, this way. Okay, so let me just remove this outline also now. So what we have, so we have this, like we had delta xn by delta t, so I'm taking delta t going to be 0, right? So we have a evolution equation for x of t, where dx dt is basically proportional to some sort of random noise, okay, and which has the following statistical properties. So this is 0, right? And if you take two time correlation, so this is usually 0, right? But only if it acts when you have the same time, right? And the strength of that is 2d. So we can summarize both these effects by putting a delta function. Okay, so this is how, like I'm almost sure that most of you guys actually know this, but still I thought, okay, we'll sort of like recap this part. Okay, so usually like, because you see that if you plot this guy, right, or if you do an experiment, let's say x of t versus t, you start from t is equal to 0, start from the origin, and you evolve this x as a function of time, right? You get some sort of one trajectory, right? If I repeat this experiment, I will get a different trajectory. Okay. So the meaningful quantity actually to quantify this kind of evolution equation is basically a probability distribution function, right? So a probability distribution function. So let's try to define that probability distribution function. So as you can see that these are two different positions, right, at the same time, right? So we can think about probability distribution, which essentially tells you the probability to find the position, the walker or the particle at position x at time t, given both of them started from some initial condition, correct? So this is my probability distribution function. Okay, and I could have this, this walker in any, in any dimension, and also in free space or any other kind of space. Okay, so usually the normalization, the way it works if you have some domain, okay, if I'm defining some arbitrary domain for the time being, we'll talk about it more in more details later on. So this should be 1, right? Okay, very good. Okay, so this was, as I said, that this was actually a random process, because every time you do this experiment, you get a different type of trajectory. And from there, we are trying to get into the evolution equation for the probability distribution, right? So how to think about it? So again, let's draw a trajectory, right? And let's say that I'm interested in the position of the walker at time t plus delta t, okay? And let's say the position of the walker there is basically x, okay? And how the walker could go to x at time t plus delta t? So it must be there somewhere, right? At time t, right? Somewhere the position, let's define it by x prime, right? And what is this x prime? So you know that this jump which it makes, that is a random jump, right? Okay, and what should be this x prime? X prime should be x minus delta x, right? And what is this delta x? Delta x is given by this quantity, okay? Okay, so we want to estimate the probability distribution that the particle was at position x at time t plus delta t, right? Given that it started from some initial condition, right? And as I said, that then exactly at delta t time before, it was somewhere x prime. Okay, one thing which I forgot to mention, you see that these are all Markovian process, okay? So if you remember this one, you see that position at the nth step depends only at the n minus 1 step, right? So this is a very important assumption. So this is something which we call Markovian assumption. So similar way, you see that I'm already invoking that assumption over here, right? I say that if I have to find the particle at position x, I need to just look into the time before at x prime, okay? So right? So let's say this is the probability distribution at time t, which is at x prime, x minus delta x, right? Okay. And what is the way actually it could make a jump? This delta x is random, right? And this randomly, if you remember that xi of n, we choose that it comes from this distribution, phi of xi, right? It could come from some random, some probability distribution, normalized probability distribution. So here also delta x, the magnitude of delta x is random. It is coming from some distribution, right? So the way we write it, so this is the distribution for this delta x, okay, normalized distribution in delta t time, okay? And then of course this jump could be anything, the magnitude of this, so I can do an average over all the possible weights of the jump, correct? Okay, and so this is done with this simple normalization property of the jump size. So please feel free to ask questions if you don't understand some part of it, okay? Yeah, okay. So the particle, you are interested to find the particle over here, right? And for that, we just need to know where the particle was exactly one step before. That is coming from the Markovian assumption. But now you see that if I draw another trajectory, it could have been here, right? So this could have been my x prime. So I have many different x primes, right? It could be somewhere else actually. And these jumps which it makes from here to here, that is random, right? And from where this randomness is coming, what is the distribution of that randomness? That is basically phi of delta t delta x. Okay? Okay. So I think so far so good. And of course, you can already see that I have invoked the Markovian condition here because it just depends on the time before. Okay. Now what you can do is, probably I will skip this part and let me just put this as a homework. So you see that I can do it for small delta x, right? I can do a Taylor series expansion of this guy, right? If I do a Taylor series expansion, so I should have p of xt something like this, right? For small delta x. Okay? Okay, so let's say that I expand this guy, the right hand side over there, and now I plug this guy over here, right? If I plug this guy over here, so what do you have on the right hand side? So right hand side I have d delta x, and then we have the first term e of xt, right? And then we have the second term we have right? I just substituted it, I didn't do anything. Okay? Okay. So what we can see here that this if you look into this integral, right? So this guy doesn't depend on delta x. So I can take this guy out. Right? So if I take this guy out, so what is left is just this, right? And what is this? 1. Right? Now let us look into the second term, right? So in the second term, I have delta x appearing here. This, as usual, doesn't depend on delta x, right? So let us leave this guy alone. And what do we have here? Delta x average, right? So this is delta x average, right? So similarly, here also you have delta x square average, right? Okay. So what I want you guys to do is to complete these steps, right? So now you can calculate delta x average from here. Okay, at least try. First try, okay? And then if you cannot, then I will help you. Then similarly, you can calculate delta x square, okay? And put all these guys together, okay? And see what you get, okay? So finally, I will give you the answer. So finally, what you should get is the diffusion equation, okay? And do this calculation up to order of delta t. Okay, ignore the delta t squared terms. Okay, so please see whether you get this term, this equation or not. Okay, so this is basically the so-called diffusion equation, Fokker-Planck equation, and there are many names for this. Okay, let us not get bothered by the names. But this is if you have a Brownian motion which has a continuous space trajectory, right? The corresponding evolution equation is given by this. So like that one, that is actually a stochastic equation, but here this one is actually a deterministic equation. right? It's a partial differential equation which you have to solve with proper initial condition and boundary conditions. Okay? Okay. So I think we have I have at least tried to cover what I wanted to do for the basics. Okay. So now I think it's a good time that we can jump to the resetting processes. Okay. So if you have any questions, okay, please feel free to ask now. Okay. If not, we can discuss during the coffee, during the tutorial, etc., etc. Okay. Okay, so as I said, to understand the resetting process, right? I mean, of course, there is a zoo of different type of resetting processes. But let us start from very simple process, okay, which is basically this diffusion equation which we had, right? And we just add resetting to that, okay? And let us try to understand how this evolution equation looks like. How can I write the, all the statistical quantities, okay? Okay, so before going there, let us first draw a trajectory. How a trajectory should look like for a diffusion for a diffusive process under resetting. Okay? Okay, so let's draw this. X of t versus t. Okay? Yeah, okay. So let's just assume that the particle, the agent, the worker, it starts from x0 at time t is equal to 0, right? And it diffuses, right? And now let's just imagine that you have a friend who is just outside, and your friend actually has a timer. Okay, what do I mean by timer? That this friend has a clock. Okay, this clock is random clock in the sense that it gives you time, okay, which is random, at random intervals. Okay, so the distribution for this clock, okay, for this time, so this is taken from some exponential form, okay, r times e to the power minus rt. In other words, what is happening is that at some rate, so I will also come to this at a later stage. What does it mean actually, this exponential time and the rate process? So what is happening is that you have a friend at some random time. This person tells you, okay, this is the time to reset. Okay, and what you do, and also imagine that you have a preferred location where you want to reset. Okay, let's just call it XR. Okay, and exactly at this point of time, wherever you are, you stop the process, stop the ongoing process, okay, and teleport the particle to this location. Okay, so what do I mean? I mean you bring this particle here in 0 time instantaneously. Okay, so you reset the particle to some position XR. Okay, from where it starts diffusing again. Okay, and then let's say again there is a random time coming from this clock, right? And at that time you decide again to stop the process and reset. So these intervals are random, right? And they're coming from this distribution. Okay? Or in other words, you can tell that this worker was moving and with certain rate r, we actually brought the particle to some initial position. Some initial position or some sort of predetermined position, okay, XR. And from here it basically keeps on evolving, this is an ongoing process which is basically going on. And then you at some point of time, you can ask, what is the position of the particle at time t? Okay, how to estimate the probability distribution of this part of this Walker or the particle whatever at time t, okay, under this resetting mechanism. Is this clear? This picture is clear. The problem statement is clear. If you understand this, that's it. We'll go through the entire school, like using this, just this schematic. Okay, so you remember that we wrote an evolution equation microscopic time, right, for diffusion equation. So the first thing would be to try something like that also for this process, right? This is something which is natural, and this is the first thing to do, right?
So what kind of physical systems show this resetting?
We'll get to that. There are many processes, okay? So for example, here you have diffusive process, which naturally doesn't do resetting, okay? So here it's some sort of a manipulated process. So you have something going on, but then you reset it. You forcefully basically bring it back, right? But there are many natural processes where resetting occurs. For example, chemical reaction, backtracking, and there are many other things, okay? Where naturally this kind of resetting occurs. But for this, just one second, but just for this diffusive process, this is indeed correct that this is a manipulated process. So you have something and you are perturbing the system by adding resetting. Yeah, please. Sorry? So for the time being, what we are assuming for the sake of simplicity that these rates are equal, okay? Which essentially will mean that all the intervals are drawn from the same distribution, okay? If you have different rates, right? If you have R1 to the minus R1, 2, then R2 to the minus, then what would mean that these intervals basically are not, the times, the waiting times, they are not statistically identical, okay? They are taken from different distribution with different parameters, okay? So x0 is the initial condition, and xr is some sort of predetermined location where I want to reset. So this.
Can we have multiple x's?
Oh yeah. You can have whatever variability you want in the system. You can have. For the timing, we are just taking a simple setup to start with. Okay. Okay. So the evolution equation, right? So I want to write basically what the position of the Walker at time t plus delta t, right? Okay. So now you can see that there are actually two possibilities, right? So let's just imagine that I was somewhere here, right? I could have continued going in this direction. That is one possibility. But instead here I did resetting, right? So at x is equal to x at time t, right, which is let's say over here. In this particular case, what happened that I came over here and instantaneously jumped, right, to this location xr. Otherwise, what would have happened is basically I could have continued in this way, okay. So this event is happening with certain probability, right, and this probability is, because this is a rate process, so I can write, so xt plus delta t is xr, okay, and this is happening with probability r times delta t. Because this is a rate process, right, if you make a jump with the rate r, so the probability is r times delta t in a short interval delta t, right? Otherwise, you would have just continued with the original Brownian motion, right? So let me just write it explicitly. So let's just write it in this way. And this one particular, this notation, you see that I have actually used this equation, okay, to write this one, okay. If this is still not clear, let me sort of like try to elaborate this. So you have here you have delta x, right? So delta x is xi of t delta t, right? Something like this, right? I just basically put it over there. And you remember that the correlation for xi t was delta function, right? And what is the unit of delta function? 1 by time, right? So in delta t interval, this should go like xi square should go like 2d by delta t, correct? So one xi should go like square root of that. Okay. So I can write and this is a random variable with the same statistical property, just that mean and variance have changed, right? Now it has 0 mean and variance is 1. This had a different variance which is governed by 2D, but now I have rescaled it, so it is basically a unitless Gaussian random variable, and you have delta t, right? So then this is square root of 2d delta t. This part is clear now? So delta x, xt plus delta t is equal to xt. This is your delta x, goes by this. Okay. So this is my evolution equation. Yeah.
Since this is a rate process,
Yeah.
where we have RDT.
Hmm.
If the distribution was not exponential,
Yeah.
it was something else.
Yeah.
Is there a function where
We have a different way of also handling this, yes. Because then it's, you know that this is, you cannot really simply write is at a constant rate. Then you have to be very careful at which interval you are looking at. So it might go as RT times delta t. So that you can sort of invoke a concept of time dependent rate. For arbitrary waiting time distribution, you can sort of like imagine that arbitrary waiting time also coming from a rate which is time dependent, okay, between intervals, okay. Unlike here what you see is a constant rate, right? But if you do not have an exponential distribution, okay, so then this rate is actually not a constant, but it can depend on time. Okay, so what I sort of try to emphasize in this case, that this is, if you are doing a simulation, right, this is the equation which you will use, okay. So given R at any microscopic delta t, you will have two probabilities. With one probability R delta t, you will reset the particle at XR, or with the complementary probability, you will just evolve the particle using simple diffusion. Clear? So all of us are on the same page? Okay, excellent. Okay, so yeah, there are. I mean, we'll come to this. Okay, the rate process, exponential distribution, these are all connected to each other very well. Okay, Poisson process. We'll see. I have something to discuss regarding that as well. Okay, so I wanted to also mention a few things over here. So let's see. Yeah. So one thing is, you see that there are actually two components of stochasticity in this process, right? Okay. One stochasticity is coming simply from the underlying process, which is basically diffusion equation, right? And then there is another stochasticity, which is a temporal stochasticity. Okay, this is coming purely because you have chosen this random time intervals, right? Okay, so there are this additional temporal stochasticity. That you should keep in mind, okay? Because moving forward, we will need to integrate out also this stochasticity, right? It cannot stay in the final equation. Also, we have to integrate it out, okay? Okay, so I think we now understand the microscopic evolution equation, okay? So what is the next step? Even in the case of diffusion, we had microscopic evolution without this, with R is equal to 0, right? The next step was to calculate the probability distribution, right? similar way, what we are going to do, we are going to write an evolution, try to write an evolution equation for the probability distribution for this particular process. Okay? Okay. So it's very important first to define a notation. So let's just define our notation in the following sense. Okay. So this is my, let me just see, like, this is, okay. Yeah, so this is, R indicates basically for resetting process, general resetting, doesn't matter. And you see that this is the probability distribution to find the particle at position x at time t, given that it started from x0 and being reset to xr. Okay, x0 and xr need not be equal. Okay, they also can come from different kind of other properties. For example, they could be they could come from different distributions and many other things. Okay. Okay. So what we are going to do is we are going to try to write an equation for this guy, right? Okay. So to do that, right? So let us just again go back here. So we are here at x at time t, right? If you look into your note, right? So what we did is we did something like this, right? We want to see that the position of the particle is at x at time t plus delta t, and now what we see, now this is the crucial step, okay? So how the particle can be at position x, okay, at time t plus delta t? It could come simply from this, right? Simple doing the diffusion process, right? But now in this case, there is an attached probability to this, right? So I have to write 1 minus r delta t, right? And then this, right, where this delta x is, you can immediately see this delta x is actually this one, right? So the average is over the distribution of delta x, right? Because delta x is a random quantity, right? This is one component. For r is equal to 0, this is what we wrote in the previous diffusion problem, right? But this, in this case, this is happening with certain probability. And what is the other one? So there is a complementary probability, r delta t, okay? So now with r delta t, right, there is a contribution also to this probability, right? But not at any arbitrary point, right? The contribution to this probability comes through resetting only if x is at xr, right? So is exactly at x is equal to xr. Only then it basically collects the contribution. Okay. And then there is also an important point. So you see that when you reset, right, the particle actually came from some arbitrary position, right? Here, there, right? So let's just call these guys x prime, okay? Different locations, but these are random quantities, right? Now you see that they are coming from arbitrary positions, right? So we should have some quantity x prime t, okay? But then I have to integrate over all this x prime, right? Because I can jump from many different kind of x primes, right? Over all the phase space. So I will just integrate over all the x prime, right? But then this is 1, okay? So this guy is actually 1. So in the final equation, I need not write this term at all. Okay? So now it is clear, right? I hope it is clear. So we are trying to write the probability distribution, the evolution equation for the probability distribution. We have one term which is coming purely from the diffusive, the diffusive motion. And then there is a complementary, with the complementary probability, all the probabilities are getting piled up at a position x is equal to xr, only at x is equal to xr. This is that term. And whenever you make a jump, you have you can jump from many different positions, but then it doesn't really matter because at the end of the day, you overall integrate over this. Okay? So this is over all the domain. Okay? So now you can ask the question, so why, like when this term can become important? This term which is now becoming 1, when this can become important? Okay? So now you can imagine that you have a resetting rate which depends on space. Okay? So it is a position dependent resetting rate. Okay? So if it is a position dependent resetting rate, so R, so let's look into this. So when it jumps, makes a jump, right? It now depends on from where it jumped, right? So it should depend on Rx prime. So if it depends on Rx prime, so this R cannot basically sit here, right? So this R has to be inside. Then you cannot ignore this term. You cannot make this unity. Okay? This is a very crucial point. Okay? There are also other cases where you cannot also neglect this term. Okay? So I'm sort of like giving you this kind of like pointers. We'll probably come to this like this kind of situations explicitly at a later stage. There is the other one was the other instance would be out of many is that let's imagine that you have some sort of a wall here somewhere. Okay? Okay? Just imagine like like let's say that just imagine that you had a wall. Okay? And it so happens that whenever the particle goes there, it sort of like like reacts with this particular wall. Okay? It gets absorbed from the system. So essentially that particle, you can forget about that particle, it is taken out of the system. Okay? So if you have also this kind of situation, okay, so then you know that whether the particle has, where from the particle has jumped, right, this x primes, right, it cannot be arbitrary, right, it can make the jump only if it is below L, right? Do you understand what I'm saying? Yeah? If it is not below L, then it is already absorbed. So it cannot really, reset. Okay? So these are the explicit cases, like when you cannot really ignore this term. You have to explicitly put this term. Okay? But for the time being, yeah. This one? This cannot be 1, right? Because the probability is not normalized because you are taking out the particle from the system. So the probability is not really normalized. There is a term for this, okay? We'll come to this, okay? Okay, so for the time being, we'll just consider this to be unity and move on, okay? Okay, so let me just erase this middle part because let that schematic stay there. Okay. Okay, so we have this one. So this is now 1, right? So what we can do in this case, right? So we can expand this, right? So P of x minus delta x, this one. So let's say that, so this is Q of so all these things are happening with probability 1 minus R delta t, right? And then you have R delta t delta x minus xr. Okay? So now when you do this exercise which I gave you for the simple diffusion equation, right? You can repeat the same exercise over here. Okay? So delta x average you can calculate, but also here you note that this This is happening with complementary probability 1 minus r delta t, right? So this delta x average is actually for the diffusive process. Okay, so this is immediately 0. Okay, similar to, because this is happening with 1 minus r delta t, right? And this will give, you will see that this will give rise to again the diffusion constant. Okay, these two will cancel, there will be d. Okay, and then there will be also delta t associated here and there. Okay, and then when you put it on the right hand side, basically take all the terms and keep only up to delta t. Okay, then eventually, and you just basically take the terms on the left hand side, right hand side, and just do like a simple like 1 or 2 lines. Finally, you will get to this equation. So you have see. Okay, so this is what you should be able to get. Okay, as you can see that this is already something which we have derived, right? And now there is this minus r times p, which is coming in, as you can see that there is minus r delta t, and when you expand this guy, there is a pr, right? So this pr I have written over here. So from there is minus rp, and then there is r delta x minus xr, which is here. Okay, so let us try to understand this equation. Okay, so this is basically the governing equation corresponding to this trajectory, right? So we have a diffusive spread, right? Right, we have a diffusive spread, but then you can see, so there is basically an outward flux, right? So basically we are losing probability here because there is a minus sign. Okay, so we are basically, what is happening is that we are losing the probability from all over the space, right? Because all these probabilities are accumulating over xr, right? So this is the loss term. Due to resetting, right, from all the x which are not equals to xr, right? And then there is a gain term exclusively at x is equal to xr. Okay, so this is the equation, you know, like which has been used, you know, like for diffusion with stochastic resetting, and this is something which was first derived by Evans and Majumdar. This, almost a decade back now. Okay, so this is the way you can interpret it, and you can see that this probability eventually at the end of the day is basically normalized, right? Because there is no loss of probability from anywhere in the space. Okay. Okay, so once you have something like this, so the next step usually would be to understand how this PRXT evolves with time, right? Yeah. So from which term? You see that we had this 1 minus r delta t, right? Times this expansion. So this r delta t times this. When you multiply and basically just accumulate the terms up to the terms which are independent of delta t, and then linear order, then delta t square, and then basically equate the left hand side and right hand side. Okay, you will see that linear order delta t, you will have this particular term.
Thank you.
Yeah. Okay. Yeah. So as I was saying that the typical interest is basically to, because it's big, you know, like you have a evolution equation similar to diffusion equation. Once you write the diffusion equation, next thing you write is you try to solve this equation, get a Gaussian propagator, right? So something similar you would like to do here, okay? But before even going there, let's try to look into the large time limit, okay? So in the large time limit, I sort of like hope that at large time limit, this term essentially disappears, okay? This is something which we call like steady state, or sometimes we call it also an equilibrium state. So there is a subtle difference, maybe I can explain it during the tutorial. So what will happen is, like this. It's always useful actually to first look into the large time limit, okay? So in this case, we hope that this P of R becomes independent of time, okay? So if PR becomes independent of time, so this becomes 0, the left hand side, right? So then one has to solve the right hand side, okay? So we have D and where this PRSS is something which stands for probability distribution steady state probability distribution, which is basically nothing but limit t going to infinity PR xt. Okay. So now this is the equation you have to solve. Yeah. A priori, it's not very simple for any arbitrary process to sort of like guess whether the process will will reach a steady state or not. Okay, for generic stochastic process. Okay, but first thing you would like to attack once you have a governing equation, first thing you would like to see that whether there is a large time limit at all or not. A simple way to understand would be like do a simulation at large time t, try to see the distribution. Okay, whether it is invariant to time. Okay, so if you look into this differential equation, right? This is an ordinary differential equation now. You see, this looks almost similar to like Schrodinger equation, right? In the presence of a Dirac delta function, right? So it should be very simple to actually calculate, right? So what you can do again, like this, I won't spend time on this. So you can solve it by yourself, okay? So what you can do is that you can write the solution at x greater than xr, right? And you can also write the solution at x less than xr. Okay, so you have two solutions, right? But then also you use the condition that probability cannot diverge at plus minus infinity, right? So some solutions, you know the drill. So some solutions basically will disappear. Only the physical terms will stay, and then at x is equal to xr, the probability should be continuous, right? So PR xr plus right, the probability should be continuous, right? But then the current or the derivative of the probability, so there we will see that there is a magnitude difference when we come from the right side and from the left hand side. Okay, that is happening because of the delta function. Okay, this is something like all of you guys know because you have solved the Schrodinger equation in the presence of delta function. Okay, so please complete this step. Okay, and I will tell you the final result. Now is the time when we can erase this. Okay. So the large time limit or the steady state. Okay. After you solve this equation systematically, so what you will get is okay. So this is the solution for this equation. Okay. So as you can see that there is a delta function, so there is a cusp at x is equal to xr, right? So let's just plot it. And away from this point, the tail is essentially exponential, right? Okay. So there are a few things which I wanted to mention here. So alpha naught is square root of r by d. Okay, and we will see that this is basically an inverse length scale. Okay, which is typically like the average distance a particle travels. Okay, between two resetting events. Okay, this is what is coming from this length scale. Okay, we'll see how this is actually how it is proportional to the length scale. I mean, you can do a simple dimension analysis, that's a different thing, but you can also systematically show it. And there are also a few things I wanted to mention. Yeah, so as you can see that there is no memory of the initial condition, right? There is, because it's the steady state, there is no memory for the initial condition. So x0 has disappeared, right, from the system. And the cusp is exactly at xr, so you see that the crucial point is exactly the resetting location where the probabilities essentially come and accumulate. Oh, so this alpha naught is square root of r by t, correct, thanks. And let's say this is the thing. This is the correct. Okay. Let's just write it in a different way. So let's say that. Yeah. Okay. Yeah. So there is also another thing which is very important here. Yeah. So you see that I'm erasing this part now. I think I'm done with this part. So this is something which is usually seen by the resetting process or the resetting mechanism is something called stabilization, right? So you see that the original process which you started with, right, the diffusion equation, right? So the solution of that was P of xt x naught, right? We had so you see that it is actually a time dependent function, right? So it basically evolves always with time, right? And suddenly when we invoke the resetting, right? So when we invoke the resetting at large time, we see that it has basically become time independent. Okay, so it seems that resetting has somehow stabilized the system. Okay, and then there is some sort of an potential, because if you look into this guy, right, it has a form like e to the power minus beta u of x, right? So beta is the temperature. So let us not call it an exact temperature. But then u of ex is essentially a particle. If you put a particle in a trap or some sort of a potential, right? So it looks like it has a typical form of that, right? Where the potential looks something like this. Something like that, right? Is it clear? I hardly see any response. Say yes, no, something. Yeah, okay. you see that this is, it seems like the particle is basically being trapped in a potential, right? But this is actually not, there is no real potential here, right? So it seems that the particle, even if it wants to, it cannot go very far. There is a typical virtual sort of boundary which is being created by this resetting mechanism. So the particle is trying to diffuse and go far, right? But then you reset the particle again and again and again, and on an average, after you look at after a long time, it seems that the particle is sort of a confined in a potential kind of thing. So there is no real potential, right? This we understand. But I'm just sort of like mimicking with the fact that, like if you look into a particle in a potential at a large time, it has the Boltzmann distribution, right? This is the Boltzmann distribution. And where it looks like this also has a similar form where U is basically replaced by this modulo X. Yeah?
What happens in higher dimensions? Do you get similar?
Yeah, you always get the cusp. See, the cusp is coming purely because of this guy, right? So because the probability is, like accumulated at X is equal to XR. So you always get a cusp. Okay, so the stabilization in the sense like you had a time dependent distribution function for the diffusion, right? And suddenly you see that the particles are now sort of like well stabilized as if under a potential, right? And is something which we call a steady state, okay? But like there is also there is a confusion always for the students that what is a steady state and what is an equilibrium state, okay? So I maybe in the last week you had a like class regarding that. I'll sort of like maybe tell you guys in a simple way. So usually when you have a Fokker-Planck equation, okay, or an evolution equation, general evolution equation, right? So you have del P, right? You can always write this guy in terms of a continuity equation. Let me just see the units. Yeah, right? So this is the continuity equation where J is the current probability flux, right? Okay? All of you guys know this equation. This is a general continuity equation, right? Now I am sort of putting the diffusion equation or our general stochastic equation, all kind of master equations, Fokker-Planck equation into this form, which I can always do, okay? So now this J is actually an important quantity. J is the probability flux or current, okay? And what I say that, let's imagine that at large time limit, right? So the left hand side disappears, right? So because P is independent of time, right? So then this guy becomes 0, the right hand side, right? So this is not an exact way of understanding this thing, but this is sort of like a more or less heuristic way to understand this, and it works very well. Now, how you can make this term 0, right? There are two ways you can make this make this term 0, right? One, right. So one is J is equal to 0, right? So whatever current you have in the system, all of them disappear, okay? Or you could have J, which is a constant in space, right? So typically, whenever all the currents disappear from the system, okay, this is something which we call equilibrium, okay? And whenever you have some current flowing into the system, okay, some constant current, this is something which we call steady state. So in both the cases, you need to like understand that the probability distribution was actually independent of time. Okay, so the current is actually a better fingerprint of whether the system is in equilibrium or in steady state. Okay, okay. So why I sort of gave you this small, small note, because in the case of resetting, what we saw is that we have a time-dependent underlying process. So I will use this word again and again, underlying process. Underlying process is the process without the resetting, okay? So we had this underlying diffusive process which had a time-dependent distribution, which basically goes in time all the way, right? Always evolving in time. First, resetting stabilized it to a time-independent state, right? Now, when you saw a time-independent state distribution, right? Now we will be, keen to know whether that was an equilibrium solution or a steady-state solution, right? And now what I did in between that, I actually compared it with a probability Boltzmann distribution, right? And say that it looks like there is an effective potential, right? So you would tend to think that this is actually a equilibrium solution, right? But as a matter of fact, this is not, okay? As you can see that there is a constant current which is being, flowing through the system, okay? Because let's do the following. So you see that we had something like this, right? So you see that with the rate, this rate is always there, okay? Even at a large time, this rate, the probability, this current will always stay, okay? And this current, in the case of resetting, so this is our resetting current, which is actually non-zero, okay? Okay, and this will always stay, okay? Even in the steadies, even in the large time limit. So this is not really an equilibrium state. This is a steady state, okay? Check what is the dimension of this guy, okay? Okay, so I think I also wanted to mention this. Yeah, I will take his and then yours. Okay, maybe yours first.
The normal diffusion equation without this resetting and all.
Yeah, this one.
Yeah. For finite systems, even that can have a steady state, right?
For?
For finite systems.
For finite systems.
Where x cannot go beyond some L or some
You're
minus
right,
L.
right. It can saturate, yes.
It can saturate and it can also give me a time-independent solution of probability.
Sure.
So this J we can divide in like two parts, which is one is reactive and another is dissipative, right? So when you say that J is equal to 0 in equilibrium, you are mainly saying this dissipative part is 0, not the reactive part?
So you see that this actually has both of them, right? Generically.
In general.
So I think what you were thinking about it, you were just thinking about this del P, del T, just coming from simple diffusion equation, right?
Yeah.
This is what it is, right? This is what you think. But you see that in this case, del P del T is never 0. You need to have a potential term to balance this, right?
Yeah.
So I'm thinking about a very general Fokker-Planck equation which also has a potential term. Okay? So the drift current and the diffusive current, they will balance each other through all the edges in the system. Okay?
There was one more question.
Yeah,
from my
please.
side. So that was like, is there any concept of like forward and backward Fokker-Planck equation in this case as well, right? I mean.
We'll get to that. We'll
Thanks.
get to that, yeah.
Thanks.
Yeah.
How do you define this resetting current from the Fokker-Planck that you wrote? Because I guess somehow you would have to treat the delta function as like
Right. So if you really want to, you see that this part, right, the current part essentially comes through the initial part of it where you have the diffusive split, right? And then there is a minus R plus R. So this is a heuristic argument essentially by saying that R has to be the current in the system because that is the one which is taking all the probabilities from arbitrary position to the resetting position, right? So this is the way we interpret R to be the resetting current.
Formally, can we treat it as like the delta function as a source at the origin?
That is what you can imagine that you are every time the particle comes at XR, as if like you are taking that particle out, putting a new particle. This is also another way of thinking about it.
Is it possible at some situation that this steady state probability, the time derivative is going to be non-zero or is going to be 0 by construction always?
Depends on, right? For in this case, it is not, right? For the diffusive process, it is not.
I mean, in the resetting process, I mean.
So in the resetting process, you are asking, are there situations where del P del T is non-zero, right? Well, for simple, this kind of, when you have this Poisson rate or this fixed rate thing, so most likely we will get to a steady state, okay? But then you could have much more complex situation. For example, I know the cases when as was mentioned at some point of time, that the distributions are not really coming from exponential distribution, but coming from some arbitrary distribution, right? Because if it comes from some arbitrary distribution, these waiting times are, right? These distributions can be very arbitrary. It could have a power law or any other kind of distributions, right, with very long tails. Okay, so in such cases, there is a priori, there is no guarantee that you will find a steady state, okay? And there is a condition also which you can derive when you are guaranteed to see a steady state, okay, for arbitrary time-dependent resetting rate. Yes?
Can you have cases where the resetting rate falls off with the distance from the reset location? So as x minus xr increases, it has less and less chance to reset here.
So that is not something, of course, you can always, cook up something like that, right? But you see that here we have R, which doesn't really couple with the where from the particle is jumping from, right? But you could also have a position-dependent resetting rate, which will have this information. So you have to give that information that as you go far and far, resetting rate is high, something like that. But for that, you have to invoke that position-dependent resetting rate in the system. In this case, resetting rate is fixed, constant, right?
But there, do you think you will have del P del T always non-zero, or would you also get a steady state? Or
okay, so, well, the way I feel, okay, so as long as you have the waiting times, which are more or less exponential, even with the space-dependent rate, you are guaranteed to see a steady state. These things, all these kind of exceptional cases will arise when you have waiting times which are not really, which have maybe broad tails or something like that. Yeah. Need not be very, need not be, like power law exactly, but could have a very large fluctuation or something like that. Yes?
Yeah. If I make dp dot is 0 artificially and try to solve the remaining differential equation, if it is not integrable, then I can say that such a system doesn't have a steady state, right?
Well, that's like you were trying to mathematically prove that whether the solution exists for the right-hand side, right?
Yeah.
I won't really call that, like a proper way to see whether there is a steady state or not. Okay. Rather, I should look for the choice of currents in the system. Going to the microscope, you can see whether there is a current which is flowing in the system. Okay, and from there try to measure it. Instead of trying to brutally solve, because there are many equations which probably you won't be able to solve it just like that.
No, yeah, but once I make dopey dot is equal to 0, what I'm left with is a differential equation for current itself, basically, right?
Yes, something like that. Yes.
Then I will be solving for the microscopic currents over here.
So you will be solving for the current like in this way, right?
Yeah.
Yeah.
Not microscopically, but these are for microscopic currents only. This equation.
Yeah, right. That is correct. But you see that there can be like many different kind of stochastic process generally, right?
Yeah.
So.
Okay. And I have one more doubt. Here we have set XR, the reset position, fixed. If I make that also random, is there any difference between this system and the normal stochastic Brownian node?
Well, of course, yes, right? Depends on what kind of distribution you are taking it, right? Because if you have an XR, which is taken from some distribution, right? So it depends on what kind of distribution you are taking for XR. Depending on that, things will change.
Okay. Let's say I take it from a Gaussian distribution, which X also ultimately follows in case of no resetting. Then wouldn't that system be exactly same as not having any reset at all?
Okay, so that's a good question. So you are saying that, okay, if I have a resetting position, right, which is also taken from some distribution, which is a Gaussian distribution. Yeah, okay. Let's see. Yeah, I think I need to think about it. Yeah?
Okay, thank you.
Okay, no problem.
Actually, it seems very
if you have the resetting to just a simple fixed Gaussian, not position dependent, sorry, not time dependent, then it is not, yes. Then you are supposed to get a steady state again back.
Even with the time-dependent Gaussian, you would have non-local jumps.
Like non-local jump in the sense?
You could have probably with a higher probability you could jump a very hard distance than by diffusion.
But you are not really assigning the resetting rate is still constant, right?
Yeah, so in regular diffusion, the probability to jump a very large distance is lower, right? Like typically. Like
Okay.
you make smaller jumps, but if you are resetting to a time-dependent Gaussian, then I could be on one end of the Gaussian and
You're
with
right.
my
You
reset
can
probably I can jump
right,
to the
right, right. So this is actually a case when you are doing the target search problem, right? We'll come to that. You'll see that if you have a target which is at a fixed distance, right? And if you are choosing your resetting distribution, okay, from some Gaussian or something like that. So a part of that distribution also like covers the target itself, right? So then it will be already by default it will be useful, like to do that. So you have to be very careful in this particular case. You have to be very careful to choose, like how you choose actually the standard deviation for this resetting Gaussian distribution. There are experiments also where people have done these kind of things. Yes.
Yeah. So the current you're talking about, I mean, initially it's related to the question that I
Yes.
asked. For the resetting process, we don't have a structure like del xj, right?
Right.
So I was wondering
Because of the singular term.
similar term.
Yes.
So I was wondering the resetting rate which you wrote is intuitively. I
Yes, it
understand
is
that-
heuristically we say that there is at least I don't know whether you can actually derive it using a continuity equation. For me, it's a heuristic understanding that this must be the current in the
But
system.
that current should be, I mean, generally J is X dependent, right?
Yeah.
Maybe,
So in the steady state, it is independent of position, at least in
but
this case.
since we don't have that structure,
Yeah.
del xj,
Yeah.
can we still say, I mean, let's say if we did an experiment where we put a wall and we compute how many times a particle is crossing there,
Mhm.
and that current might not be constant. I'm just wondering, it might not be constant. If it's very far away, it's unlikely that there are more particles, so it will be zero there and somewhere in between, let's say.
Right, that's like probably the overall current, if you would like to think about this, also incorporating the diffusive current and other kind of things, which is coming from the underlying process. There could be, like you can probably define a generalized current like that.
Are there any expressions for that? I mean,
I don't think even there is an expression for resetting current per se. This is, as I say, that this is particularly what we say, the understanding here is that to show that there exists a non-zero current, right? There is one minimal thing you can show. And it's very obvious that there is a resetting current, which has this magnitude. And immediately you can infer that this is a steady state problem.
So even for time dependent resetting, like even if it is a Gaussian distribution, so there should exist some time
Gaussian distribution in the sense, what is Gaussian distribution? The underlying process.
Yeah.
Okay.
So even for there should be some time in which system should reach the steady state.
Right.
Yeah, because that Gaussian will be achieved.
Yes.
Okay,
There are many, like facets of this problem,
Yeah,
right?
so that will okay.
Yeah. Can we have this discussion afterwards, or shall I take this? Okay. Okay. So just 1 second. I just want to. I will take your question, Harish. Yeah,
Thanks. Been asking for like 6 times.
Okay. Let's do that.
So is there so here you have 2 forms, right? An exponential and a Gaussian.
Right. This was the underlying process.
Yeah.
Right. We
Yeah.
started with, and then you got to this. Yes.
Yeah. So for a very fast resetting rate, you can kind of see that you have Gaussians.
You are not really allowing the particle to move at all, right? Like if you have very high resetting rate, so the particle is trying to diffuse between 2 resetting intervals.
Yeah.
So you are not really allowing even going far.
Yeah. What I was wondering was, is there an easy, intuitive way to see how you go from a Gaussian to an exponential?
How you go from a, yeah, there is also when we study the relaxation process, we will see how you actually go there.
And adding to what one of the questions that was asked,
Okay.
if you're resetting to a distribution which is
Yes,
itself a
yes,
Gaussian,
yes.
it would mean going back from an exponential to a Gaussian, right? If provided.
So for the, yeah, okay. So this is something which I need to think about before I answer it. Okay, so I think I wanted to also tell something else, but fine. So I think I will just end this discussion by telling you guys the following. So let's say that you are trying to calculate the mean square displacement, right? So for this process, right, eventually, so let's say that. Something like this, okay? So how it should look like, okay? Okay, so how it should look like. Okay, so for the underlying process, right, so it goes linear in time, right? So I will basically keep on going, right? But as we can see that, you know, this guy is time independent, right? So if I calculate x square over this distribution, so it should go to a fixed number, right? So with large time, as you can see that we will start from here, which is close to this, and at some point of time, basically we will saturate, okay? So this is the saturation value, so x square steady state, okay? And as I was telling that, you know, there is a length scale which is appearing here. So you'll see that this actually goes as d by r. And this is this length scale which appears here. Okay? Yeah, okay, so this is something which, let's say that we can close this here, discussion. And we'll start, we should stop it here, 10:30? Is fine, or can I continue like another 20 minutes or so? No. Okay, we'll take, huh? 4 more lectures, okay. Okay then we will stop it here. Yeah. I'm taking it to be 0. X is equal to 0, let's say. You can choose x not to be 0. It's so. Yeah, please.
So this connection with the Schrodinger equation eigenstates.
Hmm.
So it looks like you're taking the ground state.
Yeah.
Of this.
This is the ground state, right?
So in 3D, I mean, for a delta potential, the ground state is supposed to have like negative infinite energy or something like that, right? There's no bound state of finite energy in 3D. For a 3D direct delta potential. So I don't know which state.
But you see that the difference here with the Schrodinger equation, that delta function also has multiplication with the psi itself, the wave function. Okay, so
Okay.
because you have v of x psi, right? So v of x is delta, but you see that here is actually a singular term. There is no psi, there is no p attached to the delta function.
Mm-hmm. Okay, right. Okay.
So the construction wise, the differential equation essentially looks like particular, but with not it's not exact. There is no this p term, psi terms multiply with the potential.
But sorry, the same question about what is the final distribution in 3 dimensions?
So the three.
There's a Laplacian, right?
There is a Laplacian, and then you have this XR, right? XR vector. So you can show that there is a cusp around that because it's coming
No,
from.
but does one know what is the exact like?
Yeah,
PFI is,
exact distribution. We know this. Yeah, the Bessel
Bessel
function.
function.
Yes, we know this. Yes.
1 by r, I guess, right? At r equal to 0.
Yeah. And then I think in 2D it becomes logarithmic. Yeah. So when you know like start modifying the system, you also have to tell like when you are resetting to which one, right? So like as you can do, like you can sort of like come up with different models, you know, like use the methods, etc.
Stop here and then let me outside. And just one quick announcement. Today we know that we are shifting a bit early, like lunch is also early today. Do you remember the lunch time? Because we are the talk after the lunch will be I think 2 to 3:30 I guess, right?
Lunch is 12:30.
12:30 to
It starts at 2 instead of.
yeah, it starts at 2, and then there's a talk today at 4 o'clock. Okay, you are most welcome to attend the talk. And I think some of you have asked for a museum visit. Uh, so not, of course, I mean, they can, I think, take about 20 to 25 people. So you can arrange for multiple visits. So how many of you will be interested to visit today? Maybe I just put a paper here. So maybe you can just write your names. Parallelly, I think when the talk is going on, maybe we'll just also have a museum visit. So you can decide between the talk and the museum, and then you can also have an alternative visit the museum later, or
Some other day.
some other day. So just put your names here. Even if you create a riot, so we'll propose that everybody, but just put your name here so that we know how many people are interested in. Just write your, yeah.
Okay, so it's a great pleasure to welcome Dr. Ludovic Bashir from Australia, and he'll give us lectures on physics of the class transition.
Okay, thank you. Okay, so I'll try to use the blackboard. So that's indeed what I want to do. So this is what I was asked to do, so give you lectures on the statistical physics of the class transition. So I thought a little bit about what to teach. So the summer school is on statistical physics. The diversity of the lectures and probably your background is broad. So what I would like to do is try to give you the most basic features of the class transition to get started so that you understand what the problem is about. And there are many things that we could say about class transition physics, that there is a wide community of people working on this. So I decided to try and focus on what can we say and why is it interesting to work on the problem of the class transition if we like statistical physics, which I hope you all do. So the focus is I'm looking at this very wide problem with many experimental applications or questions. But I'll focus on the statistical physics questions, hoping this is what you like most. Okay, so who am I? So my name is Ludovic Berthier. So I work in France, and the research I do is really statistical mechanics. So this is why I like being here. So I work on non-equilibrium and disordered systems, and I try to apply what I know about all kinds of problems, mostly non-equilibrium kinds of models. Soft matter I really enjoy these days, active matter also, and a lot of the research is about disordered solids and what's the physics of these systems. And in all these problems, I find non-equilibrium, soft, active, amorphous, disordered. The questions that I would like to discuss with you, they come back all the time. And you take an active system, you make it dense, clack, it has a glassy behavior. You take window glasses, it is a disordered state of matter. You study an inequilibrium type of model with particle hopping on the lattice. They can undergo some kind of jamming transition. So it comes back all the time, I find, in many different fields. And I find it interesting that this problem is so general that it has applications to many types of questions. So that is also the reason why I have spent the last many years of my work thinking a lot and hard about the deep problem of the glass transition itself, and this is what I would like to share with you. So the main reason why I'm doing it myself is because it's really an important fundamental problem, first of all. And this is why I'm interested in it. I mean, I will explain in the first lecture what it means to have a liquid that transforms into glass, what are the important questions. But from the viewpoint of a statistical physicist, it's a really difficult problem because it's not a one particle problem in a complex thing. It's really a many problem leading to complex phase transitions. And those phase transitions lead to arrested or disordered or non-equilibrium states of matter. And dealing with many body physics and this complexity disorder, it's really complicated. This is why the problem still is alive, despite the fact that we've been using glasses for thousands of years. So from the viewpoint of statistical physics, it's really difficult and interesting and important problem to try and understand these questions. So that's why I like it primarily. And what I would like to do is convince you that yes, it's difficult, it's interesting, and there are many aspects of it that are useful for applications and problems. And of course, I mean, we need to raise money to do those research, or we need to think about what are the applications of this research. When you write a grant proposal and you say, I'm going to work on glasses, you don't get the money, so you need to find excuses or applications. So all kinds of applications, yes. So one aspect of it in terms of applications is what I said before. You might think that glasses are just window glasses and it's boring, but as I said, if you consider cells of bacteria or colloidal particles or polymers, and you get low temperature, large densities, they do form glasses. Sometimes they have different properties, and applications of glass physics really apply to all these broad fields from polymers to colloids to active and biological physics. So that's one way to argue that it's interesting. The other way that I would also like to show you a little bit in the lectures is even for the simple molecular glasses, that form, and we know form glasses very easily, there are still new experiments and development towards industrial applications that are really cool. And discoveries have been made in the last 10 years that I would like to share with you. And ideas for potential technological applications also exist there. And I would like to share some of this with you in the lectures as well. So that's justifications why you have lectures on the glass transition problem in that school. So just like the lecture before, I'll try to give you like a broad outline of what I would like to cover in the 5 lectures that we have. So the first lecture, which is today, will be really the basics of the glass transition. And if you adapt and learn about these things, at least you have an idea what the glass transition problem is about from different viewpoints. I'll try to, it's going to be a broad introduction. Then the second part, I will enter into the statistical mechanics of this problem of transforming between a liquid and an arrested amorphous solid. And what I would like to cover is what we now call the mean field theory of the glass transition. Okay. And it sounds boring because it sounds like mean field and it's no good or whatever. It has taken 60 years to get to the point that I would like to describe in one lecture. So I'll show you why it's difficult, what's the state of that theory, and what it can do and can't do at the moment. It's really a nice, very long story of statistical physics of disordered systems. Then, of course, it's a mean field theory, so we are not 100% sure that it applies to real systems in finite dimensions with particles. So what I'd like to do is show you a family of or families of lattice models having glassy behavior that are a little bit like the real systems, but provide you with some, first of all, interesting statistical physics, and second of all, some new mechanisms that are not necessarily easily incorporated into the mean field theory. And if you want to close the loop and compare the behavior of these simple or difficult theoretical approaches, I will tell you something about atomistic models. And I think I should stop because it's going to be too low. So atomistic models are off-lattice particle systems, sometimes extremely simple, but these things allow you also to gain some insight into the problem of the glass transition, and you can do and measure things and statistical quantities that are really interesting, and develop nice algorithms as well to simulate. And then I'm not 100% sure, but it depends how I will go in the first 4 lectures, but I have several ideas for how to close from non-equilibrium active glasses to for instance, mechanical properties of disordered solids. So I'll see how fast I go in the first 4 before deciding exactly how much I put into the 5th lecture. So that's the global outline, meaning if we go fast and you have interest in some aspect, we can talk about how to fill the 5th lecture if we can. So this is the plan. So try to understand the problem and attack it from different statistical mechanical perspectives. Okay. So as promised, this is the first lecture. So like basics of the glass transition. Okay, and I'm sorry for those of you who know a lot about the glass transition problem, but I'm going to restart from fresh, assuming that you have not really studied or read so much about it. So we start from the basics of what it is and what are the key aspects of the glass transition that then we want to attack using statistical mechanics later. Okay, so the first question we'd like to ask is, what is the problem after all? Okay. And so as I described already, I mean, I've told you about window glasses. This is a polymer glass. I mean, you have glasses even in your kitchen, in your bathroom. So basically what it is, the glass transition in practice, not in the models or in the theoretical approaches. It's really a transition between the liquid and a disordered arrested solid. So what is the glass transition? It's really this. You have a phase transition between a liquid and an arrested solid. Okay, and so just think of all these YouTube videos you have found of glass blowers taking the stuff out of the oven. It's orange, they blow, they form these shapes and everything. And as the system cools down, it's becoming more and more rigid. And at the end of the process, it's just a beautiful art object, like the shape of an animal or something. So as the system was cooling down, it was transforming between a highly viscous liquid into an arrested solid, which looks like the window glass that you have. So the transformation is mostly controlled by temperatures or density. So, and I will mostly focus on decreasing the temperature between the high temperature liquid and the low temperature solid state. Okay. You can also compress, for instance, colloidal particles. You compress them and they become also a glass, but it's just equivalent. So we'll forget about this in this lecture. So this is what we want to understand. Why is it that the system has some kind of phase transition between a liquid and a solid, and that transition, it's gradually happening as the system cools down. It's very different from what happens if you take this, you put it in the freezer, and then it's going to crystallize at 0 Celsius suddenly at 1 temperature. This is the crystallization, the transformation of water into ice. This is very different. It's just something that happens gradually, and at the end of the process, you have a solid. Very different. Okay? So this is what we want to do. So if you follow, say, I don't know, the volume of the system or something, and you slowly do this experiment that I mentioned, so you decrease the temperature, or you could increase the density. So you follow then volume versus temperature of something. So as you decrease the temperature, typically the system shrinks, and pressure would be constant, for instance. So you start from high temperature, I say, then what you have is a liquid. Okay? So that's the simple liquid state that we all know. It's just like water at ambient temperature, whatever. You decrease the temperature. I will mention it once. I never talk about it again. So for simple substances like water, what's happening at some transition, which we call Tm for T melting, the volume of the system would have a first order discontinuity, and you would have something like a crystal. Okay, so this is 0 Celsius for ambient pressure. This is liquid water suddenly transforming into ice. And you go and you have this first order phase transition towards the crystal. This is not at all what I want to talk about. So in the rest of the lectures, I'll never talk about crystals anymore. Okay, so we can forget about it. For a large number of substances, what you can do very easily using maybe different colors is you can cross the melting transition, and you can cross 0 Celsius if you wish, and you completely forget about the crystal. You don't crystallize, and you remain a liquid. Even though if you could manipulate and think, the system would like to transform into a crystal, but it takes so long that in practice you can forget about it. If you look at the glass blowers on the YouTube video, it's never happening that these silica glass suddenly transform into crystals. They never transform. They just remain liquid, and they remain liquid for very long times without thinking about the crystal. So in the rest of the lectures, I'll never talk about crystals anymore. So if you have a system that should be something that remains in another state, we call it a metastable state. So this system, it's not strictly speaking in equilibrium. It should crystallize, but in practice, it never does. And so we call that state the supercooled liquid. And so supercooled meaning it's supercooling the first order transition towards the crystal. And if you do that process, I'm changing the colors, but for most of those substances that form glasses, you don't even know where the melting transition is. You call the system, it's a liquid, it's a liquid, it's a liquid, it's a liquid. Nothing's changing really, it's just a liquid. I just use the word supercooled to remember that it should crystallize, but it does not. So what's happening to this liquid is very interesting. So in the movie of the glass blowers, you see that it's getting more and more viscous. It's more and more difficult to change the shape of this object to, transform it into something like an art object. And at the end of the process, it's becoming brittle. It's no longer flowing at all if you can only break it. And so what has happened is the system has, I'm going to use again another color. The system has transformed into a solid state. So the key difference is that this guy, it's a liquid, it's flowing, it's deforming, it has a finite viscosity. And as you cross another temperature that we call the experimental glass transition, the system is now a solid, and this is a glass. Okay. So that's it. You have your liquid, it does not crystallize, it's becoming more and more viscous, and at some temperature that I'm going to discuss in a minute, the system, it's a glass, it's really a solid. Okay, so it's no longer flowing easily, it's just breaking as a solid. And this is what you call a glass. So that's it, this is the liquid to the glass transition that we want to understand. Okay, so that's the basic aspect of it. Okay. So when the system is cooling down, is those movies that I'm talking, you're slowly decreasing the temperature because the system, the heat is dissipating into the room, so the temperature is changing, and at some point you get a glass. You could imagine having another experimental protocol where this cooling would happen much more gradually because you have like a control of the temperature cooling protocol, for instance. So if you do this and you follow the volume of the system at a slower cooling rate, you'll find something like this. The liquid is the same, the supercool liquid remains the same for some time, but as you approach here, because you're going slower, you can keep going in the liquid and you'll get a slightly different aspect of the volume. And so what I'm trying to tell you here is that the glass state that you reach when you have crossed the experimental glass transition depends in a very sensitive way of what specific history dependence you've chosen. So instead of having just one glass, I should say that you have different types of glasses, and these glasses depend on the protocol if you wish. Okay, so yeah, they are protocol dependent. And so, for instance, people can do experiments where they typically do this. They have as control parameters, say, the cooling rate. They can cool at 1 Kelvin per second, or 0.1 Kelvin per second, or 0.001 Kelvin per second. And they look at any kind of microscopic quantity there is going to be sensitive to how I prepared the system. And I'm telling you this because, of course, when you crystallize water across the melting transition, you don't care how fast or how you went to minus 5 degrees Celsius. You always have ice, and it's always the same crystal, and it's always happening at the same transition temperature. For glasses, it's very different in practice. The glasses you get depend on how you prepare them, and that's hence a very different state of matter. Yes? Okay, so what's TG? What's the nature of TG? So I'm going there. So let's say I define TG in some way for the protocol, and I was telling you if you go more slowly, then you can stay in equilibrium a bit longer before transforming into glass. I think you're asking a question: is this dashed line even well defined for one protocol? And the answer is no. It's a crossover. So people invent ways to define that thing. So you fit this, and the crossing point would be TG, but it's really a gradual thing. If I were to measure any, more complicated quantity, it's just a crossover thing. So the definition, of a crossover is just you decide that, I take this and this practical definition, I call it TG, but it's your definition. Right? Again, TM, by contrast, it's a well-defined thing. You don't need to think about how I'm going to define TM. TM is defined, and it would be the same in Bangalore and in Paris. If you go and measure TG for some substance, it's really depending on how you decide to define it. It's a crossover, so the crossover, by definition, it's not a well-defined thing. It can be sharp or a bit more less precise, but it's the only thing I can say, and we'll go there later, is the reason why the system transforms into a glass in the first place is because its time-dependent properties are changing as you decrease the temperature, and I'll show you this in a minute. And to go to your question very quickly, the dynamic properties, say the viscosity, they are changing so quickly as you decrease the temperature, so that the specific definition of TG, when do you stop moving, the speed at which you move is changing so dramatically with temperature that the particular definition doesn't really play a role. So within a few kelvins, anyone with a sensible definition of the crossover temperature would get the same answer at the end. So it's not precisely defined, but in practice, it's rather sharp.
The two sides are well defined.
Exactly.
So what is making this liquid that one of them is crystallized, the other one is?
I'm going there. So what doesn't it crystallize? I'm getting there. Okay. So I will add these questions now. So what we have is a liquid that transforms into a liquid that's not quite in equilibrium. It's only metastable. And then this not quite equilibrium system transform in a very strongly non-equilibrium way. So the fact that the system at very long times remember how it was formed is telling you that you have not forgotten history, you have not equilibrated. So remember the previous section, equilibrium is when you have forgotten the initial conditions. For glasses, you never forget your initial conditions, so you remain out of equilibrium forever. So even though this one, it's not strictly speaking in equilibrium, for all practical purposes, this is an equilibrium state of matter. Initial conditions don't matter. Time translational invariance works, everything. It's independent of the history. You go to the left, to the glass, and it's strongly out of equilibrium state of matter, okay, where you remember initial conditions, protocol, etc., etc. It's all there imprinted forever. So it means in principle, if I look into the detailed properties of this polymer glass, I should be able to tell you how it was made because it's still there. It did not evolve, okay? So that's what I mean by this. So regarding trying to come back to your questions, so that graph is giving you a hint of, what types of questions people are asking in that field. So one large crowd of people is trying to answer that question, why is it that many substances don't crystallize at all? And it's a field of research people are trying. So when you take, for instance, I do a lot of computer simulations. You take identical Lennard-Jones particles or hard spheres, you cool down the system, poof, you find the crystal. It's very easy. Then you say, I'm going to do a more complex system, and you take like 2 families of sizes, large and small particles together. You cool the system. If you choose your parameters in a broad range of size ratio, for instance, you don't crystallize. So that's what's striking, I think, is that like small minor modifications of very basic simple systems that crystallize easily are enough to prevent crystallization and give you systems that don't crystallize and instead form amorphous systems. If you look and you look at what are the real molecular, atomic, or polymeric or colloidal glasses that people study in the field are way more complicated than this binary mixture of hard spheres I mentioned. So if you know that it's so easy to prevent crystallization in the simplest system, it's no surprise that if you go to complicated molecules or colloidal system with shapes and everything, it's even harder for those systems to crystallize. So crystallization, actually, it's very easy to avoid by having a little bit of geometry, complexity, frustration in the molecules. But why exactly you need this and this size ratio to prevent crystallization? It's a field of study. People are using this. So it's an important question, and as I say, I'm not working on it. I'm not super interested, but I know it exists, and it's a good point. The bottom line is for very many substances, you can forget about the crystal and you can look at the physics of the glass transition instead.
So what is the physical difference in the atomic level between liquid and superconductor?
In this array?
In the atomic level, what is the difference like between liquid and superconductor?
0. That's what I was trying to tell you. I use different colors to remember that it should be a crystal. I give you this guy, I give you this guy, you can tell them apart. I mean, from the viewpoint of statistical physics and all correlation function structure that you can think of, you can tell the difference between the two. This one is just the continuation. And for most systems, we don't even know the crystal because we devise models that don't crystallize easily, so we don't see the crystal. And so we don't even know that the yellow curve exists, and you can't tell them apart. Well, you don't. I mean, again, if you don't know the yellow curve, you can draw the orange color at all. So if I give you a model of particles for which it's so hard to crystallize that you don't know what the melting transition is, you don't know when to use the word supercool exactly.
What about viscosity?
Yeah, so that's the rest. I will answer that question if you...
Sir, you said that the TG is protocol dependent.
Yes.
And for different circumstances, it can be different.
Yes.
But for the transition, we know at what point the transition is happening, like for the liquid to crystal transition. So over here, we know 2 phases, a metastable state and a supercool state. And we know the transition is happening. But how are you calling if we don't know a exact point the transition can happen? Like if the TG is not that well defined.
Yeah, so as I said, I mean, you need to decide how to define your TG. You have, say, you do viscosity measurements, as I'm trying to go in the next thing, and you decide that when the viscosity becomes beyond a certain threshold, you call it a glass. That's your definition of a glass. If you have another way of characterizing the system, say you do density measurements, then you'll find something like this, and you'll draw a line like this, a line like that, and you'll define TG as the crossing line. So the definition of TG will depend on how you, as an experimentalist, decide to characterize the liquid in the glass, and then you will adopt an empirical definition of TG, and you will measure it. But that depends on what your choices are. Yes, I'm going to show those things. So it's the first slide. It's the first figure. I have very many other figures. I hope I will answer some of the questions if you allow me to move on. Okay. So if I don't answer the questions, we have more times and the tutorials to get over additional questions. So this is the problem I want to tackle. Okay, so no, I was trying to list the questions, but I got stuck with the crystal. So the other series of questions are, of course, I mean, if I look at that system which is approaching the glass transition, how different is it from a simple liquid, and how do I characterize the structure and the dynamics? Because those two things are going to be what's telling me that the system is transforming into a glass. So the properties of the supercool liquid is itself like a giant difficult question that people try to understand. So of course we want to characterize this, what's really happening in practice, what is the glass transition about. And I'm telling you, well, it's a boring experimental crossover. So of course, as statistical physicists, we want to understand whether somewhere there exists something like a true phase transition between a liquid and a glass, and that's what's going to come in the second lectures. And of course, that phase transition, how is it, where is it, and how is it organized, and what's the connection between this and what we see experimentally are what we want to understand. And then I've told you already the story that if you go there, you have a solid state of matter, so I don't have to convince you. This is solid, it doesn't move. So it's as solid as a crystalline material, so ice is solid, the polymer here is solid, but they have very different structure. Ice, I know because it has the periodic arrangements of the atoms. So when you've learned before starting your PhD, you started to learn about solid state physics. You had books like, I don't know, Kittel and Ashcroft and Mermin and everything. You open that book and you go back to the outline and you look for glassy systems which are as solid as the rest of the materials. There is 0 chapter on glasses in those books because all the book is about is describing lattice structures, periodicity, groups, Bravais lattice, and everything for the structure. So it's all about periodicity. And then you go to the dynamic properties or transport properties or heat conductions or everything. And it all starts from, I have a periodic lattice, and let's look for excitations of those. So you've done the calculations of, I have atoms on lattice, and you have springs, and you look at the normal modes of everything. You've done this. And that's what the book about. It starts from periodicity. The minute you don't have periodicity because the system looks highly disordered, you're dead. None of those books are useful. You cannot understand heat transport. You cannot understand mechanical properties, vibrations, everything. You have 0. There is no textbooks on solid state properties of glasses because they are not periodic. And periodicity is the only thing we know how to treat. So of course, then, I'm trying to tell you, mechanical properties, heat conduction, phonons, elasticity, all those questions people are asking, and it's an active field of research to try and develop some understanding where the excitation are constructing from totally non-periodic disordered ground states instead of the periodic lattice that you have learned in Kittel. And so that's the broad questions that people are interested in this field. And as I said, none of it is part of textbooks because the glass transition is not well understood, the properties of solids. Of course, there are many models and suggestions and physical understanding, but we are not at the level of, the Debye theory 100 years ago for the vibrations of crystals. No, nothing like this exists. There are no simple exercise that I can do, like a 1D chain which has the behavior of the glass. Doesn't exist, for instance. So this is where we stand in glass physics, and I'm trying to convince you that there are many open questions to be understood. So I'll go into structure and dynamics of those objects. I would like to define some correlation functions to characterize first the structure of liquids and gases, to try and go into the questions you asked. How can I tell that these guys are liquids or supercool liquids or gases? So what are the functions that you need to introduce if you don't have, again, the periodicity of a lattice? You need to go back to the density. So from the positions of the particles, so you have your system. So I will probably show and sketch what a liquid or a glass looks to me. So it's a bunch of particles at large densities. And this is what a glass looks like to me. It's just a bunch of particles with no particular order. So if I want to describe that configuration, I should give you, say, the positions of the centers for all the particles in the cell, and nothing particular, no periodicity, no nothing. So out of those, of course, what I'll do is I'll construct the density field, which is just, a bunch of delta functions at the positions of the particles. And that's the density field for this disordered liquid. Okay? So the average density in the system, it's, you can write it like this if you wish. It's the volume integral of, the density over the volume. It's simply total number of particles divided by the volume. So that's, it's telling you how many particles I have in the box, and that's telling me the state of the system, or we call it sometimes the number of densities, the number of particles per unit volume. So that is telling you how many particles on average. What we want to describe is really the local organization of those systems. So what we introduce are the fluctuations. Okay, so we have delta rho of R, which is just rho of R minus rho. Okay, so from the average, I subtract the average, and what I'm left with are the fluctuations. So now I know I have nothing, then I have a particle, nothing and a particle, and I subtract the background. So to characterize the structure of liquid and system, the first thing we could look at are density two-body correlations, and this is what I would like to introduce. So we introduce 2-point functions, 2-point density correlations. Okay, so we could think of introducing a function capital G, which would be delta rho at position R times delta rho at positions R prime, and then we take an ensemble average. So R is the fluctuation of the density at position R correlated with the fluctuation of the density at position R prime. So that would be a generic 2-point correlation function. It's not the quantity we use, and we use another quantity that we like best. I wanted to do this calculation, but that's simple. So just follow me 1 second. So this rho here is the sum of all the particles. So rho minus rho 0 is what goes there times rho minus rho 0. So I have a sum minus rho 0 times a sum minus rho 0. I have, a number of terms, so the double sum I can split into the self and the different terms minus the rho 0 squared. And this is what I'm going to do, and I give you the final result. So if you write down and you put that sum into this, you develop and you reassemble the terms, what you get are something like this. It's a rho 0 times a delta function. And that's in the double sum, the I equals j term is giving you a delta function, which is not too interesting. Then it has a rho 0 squared g of R and R prime. And then it has the trivial minus rho 0 squared term. And so what I've done is I have given a name to the non-trivial part of that correlation function. I have introduced that quantity small g, and that's really the quantity that people use in liquid state theory to characterize liquids and stuff. So I just rewrite it. So these guys are vectors, and it's just the double sum I mentioned. Delta R prime minus Rj. Something like this. Tac, tac, tac. So it's the non-trivial part of the density-density correlation function. That thing is the quantity that we like. It's called the pair correlation function. And it's using this quantity that we described, liquid and super cool liquids and glassy states, at least at the level of their structure. Okay, so the physical interpretation of this is, okay, so that's a function of two vectors, but of course in the system that would be homogeneous and isotropic, that function would become just a function of the modulus and the difference. So it's a single variable function, if you wish, if you're isotropic and homogeneous. Okay. And the interpretation is just G0 of R. It's the density at point R given there is a particle at the origin. Okay? And so why is that? You see this delta function, you need to have one particle at position R and another particle at position R prime. It means I'm forcing to have one particle here, and I'm looking whether there is a particle at certain distance from myself later. So I like to think about it this way. So again, if I take my sketch of what a disordered liquid state is, it means I'm choosing one specific particle, which I called particle at 0 at the origin. Okay, so that is the particle which is at the origin. So given this particle at the origin, what is the density at a certain distance from this particle? So Java is telling you the density field that this particle is seeing when it's looking around itself. Okay, so that's the physical interpretation. And so the sketch of how it's going to look like, that function, when I'm going to plot it for this particular dense disordered assembly of sphere, is going to look like this. So typically, this function look like this. So at close to the origin, this is myself. So nobody else can sit there because I'm occupying that state. So it means there will be 0 particle close to me. Okay, so initially that thing should be 0 because of self-exclusion of the particles. So for small distances, I see 0 particle because I'm already sitting there, and so no one can sit at the same position. Now I'm going to look at larger distances, and I see that if I want to have a dense array of spheres, I will have like a dense shells of nearest neighbors, and so typically what you have is an enhanced density here. And then I'm going to continue like this. And so the finally at large distances is going to be a constant, and that constant will be, if I look at very large distances, I have lost correlations with the particle at the origin, and what I see is just the average density. So the average density being taken out of this is going to converge to 1. Okay. So that's typically what you have. And that distance typically corresponds to about 1 particle diameter. So that's the distance that I have to cover in order to see the shell of nearest neighbor. Perhaps just a little bit in my diameter, but that's it. So many things. So this is exclusion, volume exclusion. Okay, so that's the density effect. This is, in a sense, the first and the second, if you wish. That's the shells of neighbors. Okay. The fact that it goes to 1 at large distances means that at large distance I don't have long range order. So this is the sign of, Okay, if I give you the position of 1 particle at the origin, you cannot predict the positions of everybody here because the system is globally disordered. So the fact that density-density correlation functions get trivial very quickly means the system is disordered. I don't have any kind of periodic arrangement that goes to infinity. And this is in a sense, the sign that the system is liquid. It's totally disordered. There is no long-range order that propagates. And if I know the density, I know a little bit about my neighbors, but very quickly I lose the memory of this. Okay? And so the last thing that you can define for that function is perhaps, you could measure the envelope of these oscillations as you go further away. And maybe you would have some kind of exponential decay over a length scale that I call Xi static. And as I draw in that thing, very quickly after 1, 2, or 3 oscillations, those oscillations are dead, meaning that length, it's small, it's very weakly dependent on the temperature, and it's essentially given by the particle size. After just a few layers, all the memory of the local order is dead. And this is what a liquid structure looks like. Disordered at long distance, a little bit of short-range order, but that decays over a length scale that is microscopic and a bit boring. And this is how you think about those liquid states of matter. And this is how the structure of the liquid and the supercool liquid look like. And just to move forward, as you decrease the temperature, this is barely changing. It's maybe narrowing a little bit because the vibrations are a bit smaller at lower temperatures. You go into the glass, and what you have essentially is you have that structure that's frozen forever because you freeze the structure of the liquid into the glass. So that type of sketch that I've made describes the liquid well, the supercool liquid well, and the glass well, and nothing's changing almost beyond this very smooth, tiny evolution of the structure. So that's why that problem is interesting. You look at, you characterize the structure by these ways of, measuring order, disordered in systems. If you had a crystal, you would have, delta functions there. You don't. If you had large density fluctuations, inhomogeneity is developing, you would see it in, say, a growth of some correlation lengths. Nothing of the kind happens for supercool liquids undergoing glass transition. It means all the tools that people have used to study and characterize the structure of critical points, liquid gas, transition to the crystal, when you apply them to the glass transition, you see zero. You see nothing. It's boring. If you look at density fluctuations, it seems nothing's really changing as you cross and approach the glass transition and even go into the glass phase. Yes?
So also this, although the glassy phase is disordered, but you're assuming that like statistically different regions are equivalent, is it? Like when you wrote this G of R, comma, R prime is a separation of the distance.
Yes.
So statistically they are equivalent different regions.
Yes,
It's
so
a homogeneous.
what I do here, I do an ensemble average. So when I say it's the density at distance R from a particle at R equals to 0, in addition, I know I do an average over all particles. So I look at the local environment, summed over all particles, and that's the function. So what I think you're trying to say if I look at one particular function, I look its environment, or I look at another one, maybe there would be fluctuation from one particle to the next, located at the origin. But then you're looking at fluctuations inside that bracket, and it's not contained in that function. It would be fluctuations of that function if you wish. So it's a higher order correlations that you're asking at. This is just the simple two-body density. It's blind to what you said. Yes?
At TG, from the left-hand side and right-hand side of TG, is there some change that happens in G of R?
No. That's a simple one. Thank you. Okay.
So supposing I have a system which can have both the crystalline phase and the super cooled thing. So then, of course, if I did this computation where I do an ensemble average with the Gibbs distribution, then in principle I should get because the crystal has a lower free energy, I should get G of R corresponding to the crystal, right?
Yeah, but to know that there is a crystal, you should see crystal line arrangement somewhere in your system. So two cases, either the system totally crystallizes and you have your answer because it's the equilibrium state, it has a lower free energy. The intermediate case, I think this is what you were trying to suggest, is the system is crystallizing a little bit in some patches and it's remaining disordered elsewhere. And the third case is the system never shows you that there is a crystal somewhere, and if you look at the particle rearrangement, you never see the crystal. And so if you never see it in a real experiment, how do you measure the free energy of something you never saw? You can't. So if you wanted to do that thing that you're saying is, in the case where the system remains in the supercooled liquid without showing any hints of the crystal, if you wanted to compare free energies between the crystal and the liquid, you should study the free energy of your liquid as it happens experimentally. And then you should invent a way to devise an experiment or simulations where you could measure the free energy of the crystal, and then you could compare and make that decision. But if it, again, never happens experimentally, you'll never get your answer because it's impossible. You never see it. So we all believe that for most systems, there is a crystalline structure with a lower free energy. No big doubt about it. It's just that in practice, it's really difficult to go there.
But supposing just theoretically, if I could do the calculation, supposing somehow I could do a calculation, then I would always get the answer, right?
For most substances, yes.
I would get the crystalline answer.
Yes.
So that means when I do this average, I have an understanding that I'm sampling a smaller...
Exactly. So the way sometimes it's cartoon in the reviews is you have your liquid configurational space, and in a narrow corner you have the crystal. And when you do your statistical ensemble here, you forget about that narrow corner because you never go there. So it's it's not totally ergodic in the sense that that thing is not really sampled. You cut it out, and it's been validated for 60 years that if you forget about that corner of the crystal and you do an ensemble average over the disordered states, you get everything you see experimentally or numerically very well. Okay, and it's the last time that I talk about the crystal. Okay, so I need to move on a little bit. So I wanted to, someone asked about the compressibility and stuff, so I could show you, the Fourier transform of this, but probably I'm going to skip to just keep moving on. So the big question, again, is you look at pair correlation function or its Fourier transform that's being measured in, scattering experiment, the structure factor, so maybe at least I could define the structure factor once, which is 1 over n delta rho k, no time for now, delta rho minus k average. So you have your density fluctuations delta rho in real space. You go to the Fourier domain, so you get the Fourier transform of this. If you get the Fourier transform, the delta functions become exponential I, k, r, I. And then when you go delta rho in Fourier space, you get to something like 1 over n sum over I, j, I minus R, j. And this is what people measure when they do scattering experiments on liquid. It's the analog of this, and I give you the direct answer. The connection to the pair correlation function, I wanted to do it, but we can do in the tutorials perhaps. So it's not exactly the Fourier transform of Jovar, but it's related to it. Okay, so there are some small prefactors, but this is, again, that's the function that we just discussed, and this is almost its Fourier transform, and this is how people probe experimentally the structure of molecular liquids, and this guy contains density fluctuations in the Fourier domain. So someone asked about compressibility and stuff. So the compressibility for systems like this are the k going to 0 limit of this. So when you take the limit of k going to 0, you have your quantity that's called the isothermal compressibility. And so when you take k going to 0, you see that the compressibility is like an integral over the Jovar function. So again, to restate, if you had density fluctuations that were correlated over larger and larger correlation lengths, if that thing was growing quickly as you decrease the temperature, you see that when you would take that integral, you would integrate over many, many oscillations, so that integral would grow very large, and the compressibility would then be large, meaning if you have large-scale correlated density fluctuations, you also have a large compressibility. And this is what happens when you go to a standard critical point, so the liquid-gas critical point that you've learned in first year of thermodynamics. It's a critical point in the sense that density fluctuations get long range, and when they get long range, that integral is diverging, the compressibility is diverging, and that's the second order critical point that you've been taught about before. Compressibilities. I'm mentioning because someone raised the word compressibility before. Yes?
K0, if K0,
yes?
the equation above is
yeah, so it's not zero, it's really like this. You send it to zero, but you do it's like when you do an experiment, you have you have to see diffusion at finite k but not equal, and you remove the spot at the k equals to 0. So the compressibility is really defined in the limit of k going to 0, but it's different from k equals to 0.
I'm just wondering about the expansion. If you expand e to the power ik for small k, that would have just become a summation of ri minus rj, and that would be 0, right?
But
because I and j are exchangeable, and then
yeah, but then you can have all the others that you like, so I'm not sure I'd follow your viewpoint. The first term maybe is 0, but not the other ones. And anyway, in the limit of k going to 0, that quantity is really the compressibility, and that's this integral there. Okay, so no problem about that.
also, can you give a physical intuition why K0 is compressibility?
Intuition, no. I can answer that question maybe in the tutorials then. It's related to compressibility is really volume spontaneous fluctuations of the volume. So what you would need to do is a calculation of how the number of particles is fluctuating in a given volume, or how the volume of n particle is fluctuating. It's like fluctuation of thermodynamic quantities. It's Landau volume 5 of statistical physics is one of the chapters where he does this in this. And this is how you get to the point that you can relate that fluctuations in the volume are related to large-scale fluctuations of the density. Okay, that's how the number of particles fluctuating at large scale. Large scale means small k. So that's how it comes intuitively. We can derive it exactly using this formula that I shown you if you want. Okay. So that's statics. You look at the statics, it's a disordered dense system. It doesn't have interesting growing correlations. Density fluctuation looks boring, and it doesn't change as you cross the glass transition. And you see no difference between the liquid, the supercool liquid, and the glass. So if I go back to your Kittel thing, I mean, the first thing you learned about crystals is periodicity. And the very reason why crystals are solid is because of this long-range order of the particle. If I want to push that particle, I need to push all the particles there to keep the crystalline long-range order alive. And this is why when I push that table, it's moving there, right? So solidity is, in a sense, a consequence of I have a broken symmetry, I have long-range order that has developed in my system, and this is how you are taught about solidity. And now I'm telling you, look, I mean, 99% of the substances that you're using are not periodic at all. They are disordered states of matter, and yet they are solid. If I push this, this is moving as a block, and yet there is no long-range order that I have to preserve. So when I push one particle, I can do whatever I want. In principle, it doesn't have to be solid. So one of the, sometimes it's a way to make it sound very mysterious when we talk about glasses. Why on earth are these guys solid at all, despite the fact that you've cooled the liquid, you have crossed no phase transition, you didn't develop any kind of long-range order, you didn't cross any phase transition with a symmetry breaking, like Landau or Kittel or whatever. And yet, you know, the system behaves as if it had crossed a phase transition and established long-range correlation functions, and that's very mysterious. Okay. So that's why I made this big part about the structure. So what, of course, would be one answer would be fine. Maybe something like a phase transition and growing order is happening into the system, but you don't see it by your eyes. You don't see it in the two-body correlation functions of the density. And you would see it if you had more complicated correlation functions, like you suggested fluctuations of some kind, 4-point correlation functions maybe. And that's what I want to teach you in these lectures, how to look at these systems beyond two-point correlation functions to really see that, an order parameter and some kind of phase transition is at least giving rise to this glassy state of matter. Dynamics. So people talked about dynamics and viscosities and stuff. So I've told you, you look at the structure, it looks boring. So let's look at the dynamics. So now dynamics means we have, time-dependent properties. So we look at how particles move and how density fluctuations evolve in time. So the experimental analog of this, if you introduce the time, it's a time-dependent function now, and what I would have to introduce is just, the same function at time t times the density I times 0. So it's almost the same thing, but it's asking the question, imagine that I have a density fluctuation at time 0 at a given wave vector k. How is it surviving at time t later? Is this density fluctuation still there or not? And this is what people would measure when they do, again, scattering experiment, but with time-dependent properties now. So you're asking, is the density relaxing in time, and how long it takes to do so? So experimentally, that function is almost the same if you take the self part of this, and it's simpler to grasp what's happening. So again, in this function, it's a sum over I. This is a sum over I. So when I take the product, I have a sum over I, j things, which I could write. So it would be the same thing with a t and a 0 here. If I take the self part, so in this double sum, I kill the double sum, and I take the 1 over so I just sum over I now. And what I have here is Ri time t minus Ri at time 0, and I need a bracket. So just the self term in the intermediate scattering function. And most of the time, these two functions, they look really, really the same. This one has a slightly simpler interpretation that I really like. So this is the displacement of particle I between time 0 and t. You compare that displacement with a given wave vector that you decide to probe. So it would be, you would choose a length scale, a wavelength. So you compare the displacement to a wavelength, and then you take essentially the cosine of this, or the real part of this would be cosine k times delta r. So it means at time 0, that function would be 0, so the cosine would be 1. So at time 0, that function is 1. And at very large times, if the particle go to very large distances compared to the wavelengths that you probe, you would have a cosine which would be positive and negative for each particle, and average would be 0. So that function goes from 1 to 0 over a time scale that is essentially the time it takes for the particles to travel on average a distance 2 pi divided by k. So it has a simple physical interpretation. So you give yourself a given distance. If the displacement is smaller than this, the function is 1. If the displacement is larger than this distance, the correlation function is 0. So the physical interpretation, I think, is very interesting. And then if you do what was suggested before, you think about, what's happening at small scale, and you really do the expansion that you were suggesting. So you have the 1 that gives you 1. The first term, as you said, for this function would be trivially 0 for isotropic reason. And the second order term would have a k squared times delta r squared. So the average of delta r squared is a quantity that people like, in particular in colloidal physics. And the second moment would be something like this, related to this quantity, which is sum over I RIT minus RI 0. And that thing is called the mean square displacement. Okay, that's the quantity that was heavily discussed in the lecture this morning. You know, the mean square displacement of, say, a diffusing particle would get diffusive at long time, for instance. And if you do computer simulations or you do colloidal experiments where you see the particle, that's a very easy way to look at particle dynamics. And it's telling you exactly what the particles are doing on average. And people like to do and look at these quantities. So how do these functions look like? This is where I want to go. So I'm going to sketch the behavior of these two functions as you approach the glass transition from the high temperature liquid. Okay, so let me start with this function Fs, K, and T. And because things are going to change over many, many orders of magnitude, typically what we need to show is really how they relax as a function of the log of the time, not as a function of the time, because things are going to slow down over many orders of magnitude in time scale. So you start from your high temperature liquid that was, I think, white in my sketch before, and typically what you find is a simple decay. So that function I told you goes from 1 to 0 when the particles have moved the distance 2 pi divided by k, and it's essentially boring. It's happening over a microscopic time scale, okay? So that's a microscopic time scale related to, you know, molecular motion and stuff. It's boring, it's an exponential decay. So it's more interesting when you approach the glass transition and you enter the supercool regions where typically you find something like this. It's developing a more complicated shape, first of all, and that shape will be changing very dramatically as you approach the glass transition. So if you decrease the temperature further, what you see is something like this. So let me sketch it, and then I will explain. So you find that, you know, there are several features, and the first feature that you notice is something like a two-step decay. Okay, so I've tried to sketch it. So it starts decaying very quickly on this microscopic time scale, and so it means at short distance. If you remember my sketch of the particles in the box, the particle can start moving relatively freely because, you know, it's just one particle in the middle of very many. So at short times, it's very easy to move. But then you discover that you have many neighbors that are constraining your motion. And when you hit your neighbors, you have nowhere to go because you're stuck and surrounded by neighbors. So someone sitting in the middle there could not move because it's surrounded by neighbors, okay? So if you cannot move, you have to stop and you have to find your way. And the time it takes to find a way becomes very large. And when you're stopping because you keep exploring ways to go out of your initial positions, it gives rise to this intermediate plateau here. And finally, you know, you find a way to go out at much later times, and finally you go and this correlation goes to 0. So that time then becomes, so we call it tau sub alpha for historical reasons. I'm sticking to it. But what I want to say here is that this is a very short time scale, so, you know, molecular motion. And this is getting very large because we move in log scales here. And this function slows down very rapidly as the temperature is decreased. Then I told you, you keep decreasing. I'm going to take the question, just 1 minute, please. Then you go into the liquid, the glass that was, I think, red in the last case. And I told you the system is nearly frozen, so the particles don't escape anymore, and the structure doesn't relax. So if you do a measurement for this, particle never escapes. So short times, again, the particles are moving. They are looking for a way to escape from their neighborhood, but they don't find any escape route for, you know, as long as you can do your experiments. And when it doesn't relax, because it would perhaps take, you know, longer than your experiment, you decide that this is a glass. So I finish my slide and I take the question. So this is the supercooled liquid, okay? And this is the liquid. So yes, that was your question.
Plotting FSKT at some value of K.
Exactly. So you could say, so if I want to be consistent with the story I've told you, so I told you, you know, I'm looking at this tracer particle and I want to look at its motion. So in a sense, the length scale that I was probing was something like this, so 2 pi divided by k, which is about sigma. Okay. So if I probe the motion over the distance sigma, here what I've told you is I have small vibrations in this frozen arrangement. So that distance would be a fraction of sigma. And when finally I find my way out, I move larger than sigma, and then I relax the structure. And this is this second step. So yes, implicitly I had chosen a typical distance of the order of sigma. So I take your question.
It's sort of a related question. So what is basically setting the larger time scale? It varies with temperature, but I mean, do we know how to basically get the time scale?
I mean, people have been trying to answer that for 60 years, right? So I won't say, I mean, the rest of the lectures is try to give you hints about how temperature sets these very large times. It's the introduction today. So I hope I give you some hints about why and how. Why it's slow, I think, is the story I've told you, that the system is very dense, and you need to move particles a certain distance, but if you want to move, you have neighbors to move to. And that's the story that I've told you. If this guy wants to go to the bathroom, if nobody moves, he's dead. Okay?
And if
people have to open a path for him, and some kind of, a bit correlated motion has to take place. And if, they don't know that he wants to go to the bathroom, and he waits for some, spontaneous fluctuations of this guy opening, it's going to take a while.
Yeah, so observationally, if we measure the time scale as a function of temperature.
Yeah, that's the next type. So good question, but I'm going there.
Okay. So you basically anticipate that for the glassy case, right? So this tau of alpha, it will even be larger. So it essentially increases with k, is it?
Yes, I anticipate because I know. And I'm going to tell you later how it's going to evolve, and I'm trying to answer all those questions. So if you have questions like this because you discover, I hope I'm going to answer most of them in the coming figures, and if I don't, please come back.
Sir, as you said that all the particles jam goes very closer and it become very dense.
Yes.
So the flow become very slow at that point. Like it cannot flow. Is that the thing? Like are the particles not flowing or it is becoming very slow? I'm not getting that.
I'm not sure I got the question.
Sir, like you said that the particles, like when you gave us the washroom explanation, like one cannot move. So they are not able to move to another place. So are there their movement becomes slow because of this thing? That's what
I mean, that's one intuitive reason why the dynamics become slow in this dense liquid. If you want to escape, then because the density is large and nobody wants to really move spontaneously. I mean, if I want to move, this guy they have to move this way, but themselves they are caged here by other neighbors because it's a dense homogeneous system. So I told you the pair correlation function tells you the system is boring, the structure doesn't change, but it's tell you one important thing. It's looking like this crowded room with no hole. So if you want to move and you have no holes, how do you move? Right? That's the basic question, and that's why it's difficult to move at low temperatures, because everybody is happily sitting, and you want to relax. How do you do that where you have no holes? It's like these games where, you have to move particles in order to, like the traffic jam games and everything. If you have very few spaces left and you want to move that guy, you have to do very complicated things. It takes a while. Okay, so this is slowing down and I'm going to get there. I wanted to sketch you the mean square displacement, but it's really a bit redundant, so I go very quickly. So if I plot the mean square displacement, maybe in log itself, log of time. So what I told you is that at short times, the particles are exploring, short distances very quickly, and finally they will get diffusive in the liquid. I'm trying to get the colors right. If you go to the super cool liquids, where I say at short times it's easy, but then you get stuck, you'll get something like this before going diffusive at long times. And into the glass, you will explore your neighborhood a little bit, but you will never escape like this. Okay? So that's typically what's happening. And maybe to connect to what we saw before, at long times here, you will have diffusive behavior. And in d dimensions, you will have something like a diffusion constant times t. And so the mean square displacement will get diffusive with a diffusion constant as we heard before. And the key thing is that as the temperature goes down, the diffusion constant changes also very quickly. which is the analog of the change in this function here. Okay. So it was d sub s for the self-diffusion constant, so I just call it the diffusion constant to follow your notation situation. And 2 times d is 2 times the dimension. Okay. So that guy is the diffusion constant. Okay, so this is what the particles do. They quickly explore a neighborhood that's constrained, and then they wait for a longer time, which is very sensitive to how close is the temperature to the glass transition, before eventually being able to diffuse away and relax then the entire structure of the system. So at long times, particles are diffusing, density fluctuations relax, and the system indeed is able to change the configurations, and it's flowing at the macroscopic level when the particles leave their positions and explore and become diffusive, and density fluctuations relax. Then you have a finite viscosity for the system. So I'm partially getting into the question we had before about solidity. If it takes a long time, but a finite time for finally relax, the particle configurations, eventually the system will have a finite viscosity and will behave as really a liquid. Okay. So again, in the glass blower thing, you see that the stuff that comes out of the oven, it is viscous, but it's extremely viscous, and changing its shape takes some time, and the viscosity grows quickly. So one other quantity that I could perhaps introduce is the viscosity. And of course, at the experimental level, that's one of the first quantities that people have looked at in order to characterize the dynamics of the molecules in a liquid. You measure the viscosity, and by Green-Kubo arguments, you can relate that to time correlation functions and to correlation times like this. So we know actually that if you measure the temperature dependence of the viscosity or the temperature dependence of these relaxation times, essentially you get the same temperature dependence. So viscosity is like a macroscopic signature of this slow particle motion that I'm trying to describe over there. Okay. Okay, so I'm super slow, but that's fine. So what about the temperature dependence of this thing, which are the questions that people wanted to hear about? So what's the typical behavior of tau alpha? Okay, for molecular liquid, simple molecule that people have studied a lot experimentally in supercooled liquids. So you have molecular motion, you can probe the viscosity. If you want to measure molecular motion in liquids, people usually use a simple thing that you can use for molecules is you shine an electric field at a given frequency, and you look at the response of the molecular motions. So if you have a dipole attached to a particle, because it's a bit elongated, then this dielectric spectroscopy technique is telling you information about rotational motion of the small molecules. So you don't see the molecules, but you have an average measurement of the molecular motion of the at the angstrom or nanometer level. So that's the sketch I want to come to. So again, because this is changing in log, I need to plot the log of tau alpha and give you, a hint of how this is changing with as I approach the glass transition. So the typical plot that people make is they measure this in log scale to see the orders of magnitude of the growth of tau alpha. And they plot as a function of 1/t for different reasons, but one reason I like is that it's compressing the high temperature regime to this, small x region. So when t is high, this is small. So all the high temperature is compressed here, and the slow region, it's really stretched, and you see better what's happening. That's like a very empirical description of why this is interesting. So typically in the liquid, what you find is a very weak, smooth evolution of this relaxation time. And it's on that plot, it's almost looking like a straight line. So that's the liquid. And then you start to see this increase of the relaxation time, the slower and slower molecular motion, and that thing is really shooting. And the high temperature behavior that you had found stops working. And there comes a point where this is really jumping by several orders of magnitude like this. And this is typically the shape that you see. So I give you numbers for this. So if you look at, dynamics of the molecules in, that are Armstrong or a few nanometers small, typically the time scale it takes for this guy to relax is in the picoseconds range, right? This is the time scale for molecular motion in a simple fluid, in a simple liquid. So the temperature where this starts to deviate from the high temperature liquid, it has a name in our field, we like it. So we call it typically the onset. Again, it's a crossover, no good definition, but we like to call it the onset, meaning if you study glassy physics, this is where it begins to be interesting. The rest is just boring, high temperature, simple liquid physics. So onset means it's the beginning of something. And it turns out that for many, many liquid, and it's been tabulated a lot, the typical time it takes for one molecule to rotate a given angle, again, at the onset temperature is something like 10 to the minus 10 seconds. So it's a bit slower than, at very high temperature, but not so much. Okay? And then that molecular motion grows by many orders of magnitude. And I've told you we define Tg as, for instance, the time when it's getting too difficult or too slow for this particle to relax. Remember that line saying, maybe it's going to relax, but it's larger than a given time scale that I cannot reach anymore. And so people like to quote for this time scale a typical number, which is 100 seconds. Okay, 100 seconds, it's something like 2 minutes. So if you want to do a careful measurement of some, molecular quantity, and you want to extract a time scale of 2 minutes, you have to, first of all, divide the experiments, and the experiment, you want to stabilize everything, so it's going to take 10 minutes, 15 minutes to a thing. Then you'll do your measurements for 20 minutes because you want to acquire statistics, and at the end of the day, you have a fine correlation function out of which you extract the time scale of 2 minutes. If we set that threshold a bit larger, we say, okay, we are more ambitious. We could say, well, let's wait 10 times 2 minutes, so the 20 minutes, still doable. But then if you do 10 times this and this, at the end of the day, you're dead. So I think 100 seconds is like a typical time. You could do better, you could do worse, depending on your techniques and your patience, but that's setting the stage. What matters is really how many decades you've changed here, okay? And the change is a factor 10 to the 12. Okay, so if you have a better technique and you can go to 10 to the 3, you'll get 13 instead of 12, which is just, a minor change in everything. And that's, in a sense, roughly where, the experimental glass transition takes place, okay? It means at this temperature, things get so slow that if you're not careful enough, they are much slower than the duration of your experiment. Okay, just to give you, again, an idea, it seems doable to do like a 10-minute experiment. If you want to measure functions like this using, say, neutron scattering experiments in liquids, you're typically limited to up to 1 microsecond, something like this. So if you want to access those very large time scales that are doable, here you need different techniques. And people use, sometimes different techniques to collect the data over many orders of magnitude. So even though it's doable to measure this, you need to have techniques where the resolution is so long in time that you can follow the particle motion of 100 seconds from microscopic motion. So it's not easy. Okay? And so getting much longer, it's not always easy either. Okay. So many remarks on that plot. So I wanted to extract some physics as well. So what are the basic physics that we see in those plots? So we see many things. So the high temperature regime, I intentionally drew a straight line in that plot. So if you have a straight line in this, it means that the log of tau is proportional to 1 over t. So it means that tau is exponential of a constant divided by t. So this is called the Arrhenius law. And for reasons that people, I think, don't understand well, simple liquids at high temperature are well described by an Arrhenius law with some activation energy that's small. What I drew here is a curve. I didn't draw a straight line, so this is bending up as you grow. So the log of tau versus 1 over t is a function that's growing. So it means If you want to compare to something like an Arrhenius, it means that tau alpha is exponential of an energy scale that itself is changing with temperature. So if the delta here would be a constant, you would have a straight line, but the slope of that straight line is changing, so it means the apparent activation energy that you put in an Arrhenius law is changing with temperature. And so delta of T, which is the local slope of that thing, it's growing as T decreasing. So it means the Arrhenius law is broken, and sometimes people use the word super Arrhenius to describe this behavior. Okay, so many things. This huge increase of 12 orders of magnitude when things start to go slow. The way it grows with temperature, it's very non-trivial. It's faster than an Arrhenius law. So it's not a power law. It's exponential in the temperature. It's not, a power law of the temperature. And in addition, the apparent energy scale is changing as you decrease the temperature. So I want to say this and this and this. And then, of course, I think this is also one reason why the people are excited about this. If you think of the physics of an Arrhenius law, it is, I have an energy barrier to cross, like a chemical reaction, for instance, and the temperature variation comes from, if I have less and less thermal fluctuations to cross a given barrier, I'm going to go slower and slower. That's, chemical reactions, or Arrhenius was a chemist. If you think now that you have two sources for the slowing down, not only you have less thermal fluctuations, but the barriers themselves are changing. You have to understand why the barriers are changing and what's contributing to the barrier. So we are back to your question: why is it slow? How do I understand that the barriers that the particle have to cross are larger when I decrease the temperature? And so the two sources are less thermal fluctuations, but most importantly, an increase of the relaxation barriers, or the apparent ones at least. And so people are excited because if the barriers are growing, it means what I have to do in the system to relax gets more complicated. Instead of breaking, say, one bond, I have to break 2 or 3 or 4. And that number itself is slowly, gradually changing with the temperature. So it's an interesting problem. You have to cross barriers that keep changing as you decrease the temperature. So what are those barriers? What's the dynamics about? And that's the key question that has been indeed asked before. Maybe I should mention this because people do colloidal experiments. So let's think about colloidal glasses for 1 minute. Okay, so here I was telling you about molecular liquids. So the objects are, say, angstrom in order of magnitude. That's, atomic or small molecules. If you think of people doing glass physics with colloidal particles, so colloids, as you know, are much bigger particles. They're not simple molecules or atoms. And typically, they would be depending on who is doing an experiment, it would be, a fraction of a micron, up to 1 micron if you want to do colloid confocal microscope experiments and see the particles and quantify these objects. So one thing that people doing colloidal experiment gain by going to larger particles is they can see the particle motion in the dense colloidal glasses, and they can use different techniques to access the dynamics. And it's way simpler because the particles are bigger, so spatial resolution, obviously it's easier. One thing that you lose is if you think of the typical time scale in the dilute colloidal system, it's not going to be picosecond. These things are just giant compared to atoms. So the typical time scales in a relatively, the analog of a high temperature thing, the colloidal time scale, it's related to the particle size, but it would be something like, I'm using seconds, something like 10 to the minus 1 millisecond, and that time scale is essentially set by the Brownian motion we heard today. So you have a given size, you have a given amplitude for the temperature, you combine this into this molecular time scale for Brownian motion. It means even when the system is not yet dense, the macroscopic time is big because these objects are just gigantic compared to atoms. So it means I could redraw the same type of graphs for colloidal physics, but here I'm starting with 10 to the minus 3 already. And at the onset, it's going to be maybe 10 to the minus 2 or 10 to the minus 1, depending on what particular colloidal system. But these big factors are there. So this is all much slower because I have these big fat objects. And then I do my experiments, but then I need to stop when it's getting too slow. And the region where you stop, it's the same. It's your patience, it's how slow you can follow things in your experiment. So that time scale is really set by, it's an experimental limit. How long you're willing to pay or wait until you measure something. So you see that colloidal physics is pushing everything up, but not this one. So it means the range of slowing down that you can get in a colloidal experiment, it's maybe something like, so the slowing down would be like a factor 10 to the 5 in the best experiments for the smaller and that have the shortest time scale. So colloidal physics is fine, you see everything, but the amount of glassiness that you see is limited to the first 5 decades instead of 7, instead of 12. So they are missing, something like 7 orders of magnitude of the slowing down cannot be studied if you do colloidal experiments. And maybe I should show and say it also to be fair to myself. If you do ordinary computer simulations, so you take your hard spheres or your Lennard-Jones system and you say, this is an atomic system. So you could say, well, I'm really simulating a molecular liquid. So my macroscopic time scale is close to 10 to the minus 12. But now what's limiting you is really not the experimental limit. It's really the CPU time you're willing to invest in your computer simulations. So in computer simulations, you can resolve things. So sigma would be, say, 1 angstrom, and then you would have a time scale which is 10 to the minus 12 seconds. So no problem. We know how to simulate simple liquids or molecular liquids at the right time scales and length scales compared to this. But now the limit is CPU time. Okay. And so in conventional simulations, if you're willing to spend, say, a week of equilibration running the things, typically the slowing down that you will be also reporting by some magics, it's about a factor 10 to the 5 too. Okay? That means you can do this, but then this is the CPU limit. After 1 week or 2 weeks or months, you stop there because you cannot do. And again, you can only cover so much of the slowing down of the dynamics compared to experimental systems. So there are many things we can do with colloidal glasses or computer simulations, but still there are these 7 orders of magnitude missing towards the experimental glass transition and molecular liquid. So that region here, so 2 views are where nothing really changes. So what you learn on that part of the branch will extrapolate to TG and nothing new is going to happen. That's one way. The other way is, well, so fine, you can study a little bit of the glassy dynamics, but you are missing totally all the action to explain, slow molecular motion in real molecular liquids at the glass transition. So these are the 2 possible views. I think both are a bit true and a bit wrong, of course. And it's an open question actually in the field these days is, have we learned everything so far because we were using those techniques and we can resolve in space and time all the motion we like, or there are new things to be measured, and experimentalists in the field of the glass transition are still trying to develop techniques to quantify these relaxation times to these very large time scales, resolving molecular motions as much as they can over a length scale that are super small. And the decision is still open whether, comparison between this, and this is going to give you the same results or not. But that's, I think, an interesting question. I think I need to stop and maybe take a few questions before going to lunch. And I'll restart from there. I had more things to say about that graph, but I think it's better to stop for now, take a few questions, and then we lunch. Thank you. So I take a student and then you.
Yeah. Initially you said we need at least a binary mixture to get this glass configurations and simulations. In real life also, it should be the same case, right?
In what, sorry? In?
To get this, to make glasses from liquids by temperature protocols, we need binary mixtures, right?
For instance, yes.
If it is a monodisperse collection of balls, then would it crystallize automatically or something?
Yes, that's what I said. I mean, if you take, actually, when we do computer simulations of simple system, particles are not even balls, they are point particles with a specific pair interactions between them. So they are points, actually. So what I think we know is that if we take points with pair interactions that are totally monodisperse, so all pairs are the same, it's very difficult to avoid the crystal. Yet, as soon as you move out of this regime, it is very easy to devise computer simulations where you don't crystallize at all, never. And in reality, I think when people do colloidal glasses, by definition, colloids are objects that you create chemically. So they are not all the same. So again, it's very easy for colloidal people to avoid crystallization. And maybe that was the question you were hinting. If not, I think I phrase it for you. If you consider molecular liquids and you say, I'm going to look at the glass transition of glycerol or whatever organic molecules, then here all the glycerol molecules are born equal. They are, it's just chemistry. You have some atoms and that's it. And it's true that in most molecular liquids, you don't need mixtures of glycerol and ethanol to avoid crystallization. Each one of them can be a good glass former. So the simplest substance, I don't know, argon or whatever, they crystallize easily. You go to slightly more complicated molecules, that's it, you get glass transitions very easily, even though all molecules are the same. But then there are molecules, they are objects, they have a shape, they are not the points particles that we get. So people doing computer simulations, I think, are trying to move away from point particles, sometimes to answer questions related to, say, moleculars and shapes. The status is we believe that the simplest model with points with a little bit of polydispersity, for instance, and the slightly more complicated shapes, they would, we think, but no proof, that they have essentially the same physics, and then provided you don't crystallize, then the glass transition physics is unaffected. Right now I have a PhD student who is trying to do beyond point particles, and we have 3 particles in a triangle, for instance. It's looking like one of those simple molecules called the orthoterphenyl. And it's true, you take 3 particles connected by springs like this, the springs can move, the particles are all the same, you put them into your box, they don't crystallize. So all the particles, all the molecules, are identical. It's a small, evolution compared to the one particle case, and yet it doesn't crystallize and it's going to look like the molecular liquid. And we believe that the physics is really a little bit independent of those details.
Okay. One more question. This dynamic structure factor that you have given, f of k comma t, that also characterizes the dispersion of sound waves in any given material, right?
Let me see. Yeah, so the way I describe the correlation function, the intermediate, I was thinking of k is fixed at a few sigma, as we said, and you look at very, very long times. When the physics you're talking about is I'm looking at extremely short times and a variation of length scales across from super small to very large. But yes, it's about the same function, yes. A different regime of time scales and length scales, that's what I'm saying.
So can I tell the difference between a glass and a crystal just by hitting it with my finger or something? And characterizing the sound waves.
People have been, working hard on trying to understand, if you think of the glass as a solid, then you want to characterize the speed of sound and, the density of state and how it's going to scatter light. And that's a gigantic box that I'm not going to cover here. And one thing you could say is that I've told you you know, locally it's disordered, it's not periodic. But if you think of, I'm going to look at length scales much larger than the particle scale, what I'm going to see is probably a continuous elastic medium.
Yeah.
And so it's probably true that a large enough length scale, so small enough wave vectors, I forget about the details of the molecular arrangements, and some of the elasticity, speed of sound things that you know, on those length scale will be like a crystal because you forgot about you've of course grained the system large enough that you don't remember what's underneath. However, if you start to probe length scales that start to feel that locally you're disordered, you'll see deviation from the crystal in everything you want to measure: dispersion relations, the connections between density and everything, the temperature dependence of the speed of sound, temperature dependence of even the specific heat is different, provided you probe in the right regime of time scales and length scales.
All right, thank you.
So I don't have a precise answer. It depends on the question.
Yeah.
Yeah, so usually in chemical reactions, right, like the activation barriers usually are not dependent on temperature.
Yes.
Right. So here you are saying that this activation barriers are becoming function of temperature. This is basically are these fictitious barriers which are being created by the particles when they're doing this dynamics?
We don't know is the honest answer. So I gave the RNUs precisely to shock you, to say, well, what's happening? I mean, in some very few liquids, like precisely window glasses, it's silica glasses with strong bonds between the Si and the oxygen molecules. And essentially, if you look at, if you want to break a bond and reform one, it's costing you a lot of energy because these particles really want to form bonds. And it's almost giving you the temperature dependence of this, because for those systems, the relaxation time is like this, and very quickly it goes to something like this, and it's almost homogeneous in very few cases, and we call them strong glasses. They're different. And in those strong glasses, typically you have these strong bonds between particles, and breaking a bond and reforming one almost give you the temperature dependence of the viscosity. And then the Arrhenius picture of a chemical reaction almost works. Nobody knows for sure how silica glasses relax there, but that's at least a physical picture. It means if everything I have to do is really a lot, and then from there it's easy, it's dominated by a large barrier, it's almost like a chemical reaction over a fixed landscape. But for most glasses, it's very different. First of all, there are no strong bonds. You have Lennard-Jones particles, etc. And the effective thing you have to do keeps changing. So what you have to do changes as you decrease the temperature. And then, as you say, the analogy with anything chemical-like, it's dead. And what I want to do next is give you at least ideas that things like this exist in some simpler cases we know.
Thanks.
Okay, so I think maybe we have to stop now.
Oh, okay. Sorry.
Yeah.
You can ask me the question during lunchtime.
In the lunchtime and tutorials. So now I think we have to quickly go for lunch. And we were supposed to meet at 1:30, but maybe we'll meet at 1:45. So we start at 1:45, the next lectures.
Who's this?
Mic. Wireless. So I'll connect it.
Yeah, how's it going?
You have just arrived or?
I just arrived actually. My problem was I just flew in from Geneva yesterday, and then I didn't want to. If I had thought a little more intelligently, I would have flown directly from Geneva to here. And but these are all unconnected events, so I wasn't thinking about them. And it was a personal trip, and this was not. So that's why I wrote to Abhishek and you and requested.
No, that one is not a problem. So you still have jet lag or?
Yes.
So you checked in the guest house, right?
Yeah, no, they brought me here to the guest house. I just had just some organization, and then I came here.
Yeah, your flight is arriving 11:30 or something. Okay, so we'll go to the next set of lectures now. So this is by Professor Ram Ramaswamy. So he's currently at IIT Delhi. So he is going to talk about the collective dynamics of complex systems.
Okay, good afternoon. This set of lectures is in some sense complementary to what you've been hearing from Professor Sitabra Sinha last week. I had a word with him yesterday, and I understand that there's a little bit of an overlap. So what I hope to do in these, in the set of 5 lectures is to study and discuss the dynamics of coupled systems, focusing mostly on oscillators. Right, so I would be looking at the behavior of ensembles of dynamical systems with a lot of emphasis on the dynamics. And one of the reasons we look at oscillators is that we want eventually all the motion to be bound and confined. So, of course, one could consider just free particles, which is more common in statistical mechanics. Gases, just arbitrary particles moving around. But I would rather look at the dynamical question, we consider motion that is somehow confined. And a good model is to look at oscillators because you have both periodic oscillators as well as aperiodic or chaotic oscillators. So the nature of the motion is not confined to being necessarily regular. You can have really complicated motion even though it is essentially oscillatory. Okay. Now, one of the discoveries of the last century is that simple systems with simple equations of motion can have very complicated dynamics. And another discovery is that the collective behavior in such systems can actually show a remarkable wealth of different phenomena. And this includes global synchronization. And there are many, many variations of this process of global synchronization. there's something called amplitude death, which I will discuss. There's a phenomenon known as aging or stasis, which happens in heterogeneous ensembles, because looking at dynamical ensembles, one looks at both homogeneous as well as heterogeneous ones. Then there's very interesting behavior of coexisting mixed kinds of dynamical states known as chimeras. And this is essentially a spontaneous symmetry breaking of a dynamical symmetry and ensembles of interacting oscillators. So over the course of lectures, I hope to cover all these various topics with, as I said, an emphasis on dynamics. The actual lecture plan is as follows. Today, I will tell you a little about synchrony, phase locking, the observations of synchrony, and in fact, some amount of the historical development. Tomorrow, I will discuss a very important model in connecting dynamics and statistical mechanics, the Kuramoto model. I know that you have already been introduced to it somewhat. I will reintroduce the problem. The third lecture will be largely devoted to the phenomenon of synchronization in chaotic systems, what it means for a chaotic system to synchronize. There's the notion of of the synchronization manifold and generalized synchrony, and I will cover these various topics. The fourth lecture will be on oscillation death, stasis. Oscillation death, despite the macabre name, refers to the fact that oscillations stop. So systems stop oscillating and just go to fixed points. The phenomenon of stasis and the behavior of heterogeneous ensembles. And finally, I will talk about dynamical chimeras on the last of these lectures. Okay. Synchrony, the phenomenon of synchronization, is probably, I would say, the most common forms of visible collective behavior that is seen in nature. There are all sorts of other collective behaviors that you all are familiar with, but synchronization, meaning at the same time, is one of the most common kinds of collective behavior that we see. Many examples of synchronization are known in biology, which is a phenomenon of much interest. And these range from, complicated examples that go to, the spiking of neurons associated with memory, to much simpler examples, such as people clapping in unison in a performance or something like that. There's the phenomenon of people walking together. They fall in step with each other, walk in gait. This is synchronized gaits that people have. You have, most commonly, because we derive so much of our energy from the sun, almost every organism on this planet has what's called a circadian rhythm. That is a rhythm of approximately 24 hours. That is circa and dia, so approximately 24 hours. And the circadian rhythm is necessary for cells to actually utilize some of the energy that is available through sunlight or through light, basically. Okay, so this is, and not to put too fine a point on it, most of us get up at roughly similar times when the sun rises and go to sleep when the sun sets. So our bodies are tuned to the same circadian rhythm, and this is an example of a synchronization phenomenon. All right. Now, which gets covered also in the various kinds of synchronization that people talk about these days. One early example of the synchronization of animal species was a famous visit by an explorer to the jungles of Malaysia a few centuries ago. And this is a video from a recent time, of course. But what you see over here is a group of fireflies, those insects over there. And these fireflies send out flashes. You've seen jugnus in India, but this is a species-dependent phenomenon. Not every species does this. So in Malaysia and in other parts of the world, these fireflies respond to each other's flashing. Only the males flash. They do it only to attract the females of the species. And when one male flashes, other males also flash until, as you see over here, the whole ensemble. Oops. Eesh. 1 second. Okay. Okay, so you see larger and larger groups of them flashing together. Now it's sort of almost the whole tree. And actually, some people have described it as being truly spectacular. When you see it, the tree goes on and off and on and off. I mean, Diwali lights, etc., all sorts of analogies come to mind. But there are other phenomena that can also be seen as some sort of synchronization, and those are in current physics context quite interesting. One of them is to do with the schooling of fish. You've got large groups of fish which have phases, if you like, of individual random motion where they are just moving around. And then you have this kind of group collective motion where each one of these fish, the motion of each fish is very highly correlated with that of all the others. So the flashing fireflies were synchronization in time, right? Here there is not only a synchronization in time, but also in space. And this other sort of now, again, very commonly studied example of murmurations, or groups of birds that are flying together. These all come under the discussion of active matter and so on and so forth. Okay, so what I show on the right over there is a picture drawn by an artist, often, just a static shot of this kind of view. And you can see certainly that there is, there are patterns that have formed in both space and obviously in time, because they're all flying together and not colliding with one another. Okay, so soon the velocities get completely correlated, directions get completely correlated, and all of them are acting, it's sort of common to describe this as a single superorganism. So this is an example of spatio and temporal synchronization. All right. Now, this phenomenon is actually quite common, and but it was not until the 1600s that Huygens described it explicitly. People have seen phenomena, people were aware of the similarity in time or synchrony, but Huygens was the first to have mentioned this explicitly. As you'll probably know, Huygens invented the first accurate, or first reasonably accurate clock, pendulum clock. In a very clever construction where there was energy supplied to the clock by the winding of a key, and then the clock was kept, absolutely so precise timekeeping through a bunch of different I mean, those mechanisms, it's a complicated story of how he did all that. Okay. But once when he was unwell and convalescing from some kind of fever, he was in a room where the clocks were kept, and here is an example of the geometry. There were two pendulum clocks suspended from a common support, and what he observed was that pretty soon these pendula they got into a certain what he called sympathetic movement. Okay, so the pendulum, as you know, each pendulum is oscillating, and sort of, okay, so the extremum over here is D, C, F, G. This one is E, D, and K. So what he noticed was that if you put these two pendulums one next to the other, suspended from a common support, after a certain amount of time, and it depended on how you set it off and the initial conditions and so on, but after a certain amount of time, pendulum A, for example, when it was at position D, pendulum B was at K, and then this would swing inwards to position E, and this would swing inwards to position G, and then this whole cycle would repeat. So A was correlated with K, and then this would, D was correlated with K, and then it would come to G, and this would come to E, and so on and so forth. Right. So they would be just going, sort of swinging in what is now called antiphase synchronization. Now, these were pendulums that were designed to keep time on a ship, right? Some of you may be familiar with this problem that mapping the longitude was a major, major preoccupation of clockmakers and shipbuilders and navigators all through the 1600s. It was one of the difficult problems. Latitude was much easier solved because the latitude told you the length of the day. So as you moved up in latitude, you were getting progressively longer or shorter days, depending on which way, the season of the time. But the longitude was very difficult, and that required very accurate timekeeping. So these were accurate timekeepers, and therefore the basic pendulum had almost the same oscillation frequency. Not identical, because no two objects that are constructed are precisely identical. They can only be mathematically identical. So what Huygens was worried about was that why is this happening? First he thought it was the air pressure in the room, that the wind was causing them to synchronize and so on and so forth. But eventually he figured out that what was actually happening was that because they were on a common support, it is the small motions of the support that cause these two to synchronize. Okay. So the basic idea is still valid today. You take two systems that are not too different from one another, if they are oscillating, and you couple them in some way, they will synchronize. Okay? Well, they will not always synchronize. We'll see some of the ramifications of that, but the basic physics idea is there. Right? Okay. Now, in all his experiments, Huygens mostly observed this antiphase synchrony, namely the phases of oscillation of the two oscillators, the two pendula, were exactly opposite to one another. So they came together and went apart, and came together and went apart. This was the way in which inevitably these two pendula would synchronize. There is, however, another state, and if you recall your classical mechanics, normal modes, etc., you know that there is one mode where the oscillations are in the same phase. Okay, so there is the state of in-phase sync, and there is the state of anti-phase sync. And Huygens inevitably observed the anti-phase synchrony, right? Which seems to suggest that, look, there is, in addition to this whole phenomenon of synchronization, there is also the question of stability of what you observe. So maybe this the anti-phase synchronization state is just much more stable than the in-phase synchronization state. Okay, this is just a depiction of the two. Now, because we can redo all these experiments, in around about 2000 or so, a group which involved Kurt Wiesenfeld and others did this experiment. And this is, it's a lovely paper which I will give you all the references to and so on, where they took two pendula. It's a little important that it's not just the, you couldn't do this experiment again with this hanging, just an arbitrary pendulum. You need a little bit of the Huygens mechanism for keeping fixed time. So in particular, there's a thing called the escapement, which was very, there was a design element. You look at the design and you just sort of marvel at the mind that made that design. So here you have these two pendula which are set off at arbitrary times, and they are on a common beam over there. Okay, so part of this is the construction, because it's supported over here with a heavy lead weight, and you've got a common beam and these two pendula. And after a while, and you can see, it's not a great photograph, but you can see that this is, these two are correlated, and at earlier times, this one has been over here and this one has been over here. You see the anti-phase synchronization coming out. Okay? So you can do the same experiment, and you can, and actually it's not just seeing it when he was recovering from some illness. Huygens was a great experimentalist. He actually did many, many days of experimentation trying to figure out what was going on with partly because he was interested in synchronization. Yeah? This is the asymptotic behavior. You start with some arbitrary initial conditions. You want to know what happens at long time. At long time, they will go anti-phase. Okay, in the language of dynamical systems, the anti-phase state is an attractor of the dynamics. Yeah.
So the total energy of the two oscillators are not preserved?
Well, you see, you don't, a simple oscillator in air will damp. So you need to keep providing energy to it. The whole description is non-Hamiltonian. Right? So we will have essentially damped oscillations, but they're also forced. That's what the winding of the clock does to, it provides energy. And so, yeah. Okay. I seem to have broken this. Oops, no. Okay. Now you can do a variation of the Huygens experiment. Instead of having the pendulums hanging from your beam, you can put a bunch of metronome clocks. Okay, you get the point, or maybe some of the points. All right, I just picked this out of the internet somewhere. There are many, many examples of this. But it turns out that the metronome clock is sort of like Huygens and sort of not. Okay, the way in which it is sort of like Huygens is that it is a pendulum. Each metronome is a pendulum. It's an inverted pendulum, and it's an inverted pendulum which is wound up, so you're providing energy to it, and I'll go back, but let me tell you what are the things I'd like you to look at in the next partial re-demonstration of the same video. All right? You see, the period of oscillation is fixed by where this weight is put. Right? So effectively the length of the pendulum is adjusted by shifting this bob on the metronome. Right? So, okay, so these are actually of almost all the same length, right? And we are doing this with 4 or with 2. I mean, it hardly matters actually, but you can do, and you can look for videos on YouTube where you have 1,000 or 1,000,000 or what, not 1,000,000. I don't think anyone has the energy to wind up 1,000,000 such things, but definitely I've seen pictures of 1,000 or so. It turns out that this will reduce to the Kuromoto model, which I hope to discuss with you either today or tomorrow, perhaps. All right? Yeah? See, what you don't, this is not a great video, but over here or on the back, there is a chabi bhardo. Right? I mean, I actually have a bunch of these in my lab. I used to have a bunch of these in my lab in JNU. And we would just sort of routinely wind them up. But the problem is that these don't last for very long. So it's an energy input mechanism. It's a wound spring. All right? The feature that you want out of this is that it will oscillate with the same, with the same frequency. That is what we want. Okay, and then I'd also like you to see the difference between the Huygens and this, namely that the Huygens is hanging and whatever motion is happening is there, it's fixed. Whereas over here, this is on a swing. So you can see the base of this moving around, right? If I had had the foresight, I would have actually brought a few pendulums, a few metronomes along. They're easier to carry than pendula, all right? So that's why it's nice to do the experiments with them also. But okay, right? And you can see that there are just a group of them on a base, and they will communicate with one another. And let me, okay. And the other thing is that you can watch this video with your eyes closed. Because you can figure out, where the oscillations are happening just by the sound. So let me just go through that, because there's one point I want you to get, which I'll mention. So they are started off randomly, and they don't have, now it's getting closer and closer. This is the antiphase state. Now in phase, but not very stable. It's going out. And the gap between the ticks is getting, now it's periodic. Now it's in phase, it's going to stay there for a while, at least until they start running out of energy. Okay, so one can do a lot of experiments with this, just taking audio recordings, video recordings, and so on and so forth. Because here you've got a system which is actually, sorry, let me just, the last point about this, because I'm going to come back to it a little later, right? An important thing about an oscillator is, to describe an oscillator, you need an amplitude and a phase. So you have the amplitude of oscillation, which more or less tells you how how far it goes from some central position, and the phase of oscillation, namely how, something which describes how it goes around in space, or in phase space, actually. Some of these ideas we'll sort of talk about. Okay, so let me just talk about entrainment. What you saw is sets of pendula with frequencies that were almost the same, starting to behave identically. Okay, so frequencies were almost the same, and then they became the same. Now, the same of the first part and the same of the second part need not be identical. Namely, coupling between these systems alters each system imperceptibly, and the final actual common frequency that they are oscillating at could be different from the non-interacting situation. Okay, just keeping that in mind. Now, when you have systems which are oscillating at different frequencies, it's not just that they will start behaving identically when you have the same or nearly the same frequency. So if one frequency of oscillation is omega 1 and the other is omega 2, what I showed you was the case of omega 1 by omega 2 approximately 1. But instead of being approximately 1, if it were P by Q, where P and Q are integers, even so you find this, that the two systems mutually entrain each other. Okay? And this can be, am I making myself clear? Yeah? All right. So particularly these give rise to, these are important in phenomena like resonances, right? Where if omega 1 by omega 2 is equal to 1 by 2, there's a 1:2 resonance, then there's something interesting that happens. Okay? We exploit such resonances and such, particularly when we are on a swing. People remember being on a swing? Jhula? Yeah? Not just sitting over there and getting pushed. Okay, how many of you have done anything more than sitting on a swing and getting pushed? i.e. standing and autonomously driving the swing into a state of oscillation. Okay? So if you've done that, then you will know that there is a very special technique that one has to employ in order to pump the pendulum with enough energy so that it swings, right? And it mostly involves changing the center of gravity of the swing, right? So the effective length of the swing is changed by the person, right, standing up and crouching on the swing. Yeah? All right. Now this kind of changing the center of gravity is done in a very specific way. Yes? Huh?
I have a kid. So
You have a kid, so you have seen it. No, the point that I want to make is that the 1:2 resonance is actually exploited over there. All right? The frequency of oscillation of your swing and the frequency of your getting up and sitting down is exactly in the ratio of 1:2. If it was not 1:2, you would not get the pumping effect. Right? So this is also called parametric resonance. It's a common and well-studied phenomenon. In fact, it's a way of transferring energy from one system to another. People do it all the time in accelerators and all sorts of places. People use this basic phenomenon. But what is interesting is that the 1:2 resonance is what we naturally employ. All right? It's very difficult to do the 1:1. It doesn't come, quote unquote, naturally, but that should also work. That is, you stand up at one end of your swinging and you sit down at the other end of your, see what you do is that stand up at the two edges of the swinging. and at this bottom part you sit down, right? That's how it's usually done, or I think vice versa. No, you've got to be there in some sense, right? So you've got you're sitting down at these two ends, you're standing up in the middle. In principle, you could sit down over here and then rise over here and then sit down again and rise. You could do it the other way. So you can exploit the 1:1 resonance. Next time you're in a park and you see an unattended swing, go for it. Could also, huh? Kids do 1:1 actually. Kids do 1:1?
They raise the leg and then they put the leg while coming back. So they don't stand up and rise down. So they do this way.
Sanjeev, you do it. All right. No, yeah.
If resonant frequency is exploited by 1/1, then rope will break, no?
The rope will break because it's too much energy that goes in.
Yeah. So it has to be less than 1.
If it's 1, no, I was going to actually suggest that you all do 1:4. Because that should also be possible, in the sense that all these are resonances that can be exploited. Nevertheless, if you've got two oscillators with frequencies in the ratio of approximately 1, what we saw right now is that they entrain one another. That was what we saw in the metronome case, right? But this phenomenon is actually more general, and I'd like to at least introduce you to the idea of circle maps, right? Yeah? Yeah, I mean, 1:2 is most efficient. We'll just see, we'll see in a moment why. All right? Okay. Now, a simple pendulum can be represented by a circular orbit in the plane, which is the phase space. Okay, so the variable for the pendulum is theta and theta dot. Okay. Okay, so if you've got if this is your pendulum variable theta, then if I plot theta versus theta dot, then the oscillation is basically described as a circular orbit in the phase plane. Yeah? This is sort of common from any course in classical mechanics, right? Okay. Now, if you take a single pendulum, it's a circular orbit, and a pair of pendula that are uncoupled with each other would actually be represented by one circle for one of them and another circle for another of them, right? And the frequencies of the two, let me call them, if this is omega 1, this just tells you how I go around the circle over here. And similarly, I would have another oscillation with frequency omega 2. Right. Now, representing them together in a common phase space has now got dimension 4, and each one of these is on a circular orbit, so the pair of them together are on a torus, right? And that is, okay, so that's a representation of the torus. Now, if omega 1 and omega 2 are rationally related, then after a certain amount of time, which would be q times the basic frequency, basic period in one direction or the other, I mean, one can work that out, the orbit will be closed. The orbit will close upon itself. Right? Stay with me. I mean, the fact that if omega 1 by omega 2 is rational, you get a periodic orbit because at some point in time, everything comes back to the initial condition. Right? Because
one thing, how do you, where is the torus coming from? It looks like, how is this four-dimensional phase space?
the torus comes because you've got a circle in one dimension, it's S1, and there is another S1, it's S1 cross S1, so that's T2, right? The point I just want to make is that the orbit, it's a joint orbit if I'm thinking about it, that is going to go around and then come back to itself after a certain amount of time. It'll depend on those integers P and Q, right? Okay, so you'll have a closed or a periodic orbit in the case of a rational relation between the two frequencies, all right? Okay. The period of one is going to be 2 pi upon omega 1. The period of the other is 2 pi upon omega 2. So at some point in time, you'll find that P times 2 pi over omega 1 is equal to Q times P. The two of them will match. Okay? Right. On the other hand, if omega 2 by omega 1 is not a rational number, then the orbit will not actually close on itself, but it will just keep winding around incessantly, right? Okay. Now, the difference between these two situations is actually most easily seen on a slice through this torus in what's called a Poincare section. Okay, so in this four-dimensional phase space, if I just take a plane and I slice through that, then what I see of a torus is a circle. And each time this orbit passes this plane, I will see a point. Okay? If you've not been introduced to the idea of a Poincare section before, just take a moment and we can just repeat that. What I'm trying to do is, you see, this object is in four-dimensional phase space. I want to visualize it on the plane because I want to just see a section of it. So what I've done is to cut through the torus at some arbitrary point, and I'm just going to mark the point when the orbit will pass that particular plane, right? So the image of the torus is going to be a circle, and each time I pass around, I'm going to just keep noticing where it cuts this particular point, and I'm going to observe it. Yeah? All right. Having done that, essentially what I get is a new representation of this joint motion. This theta is not the theta of the pendulum, please. Okay? This is the theta of, see what I've done is I have the torus. I cut through this torus over here on this section, and when I cut through that section, I get basically the Poincare section, right? The image of the torus that is left behind is a circle, and each time my orbit passes through this particular plane, I will get a set of points. Yeah? A little algebra will show you that the way in which the points keep going around basically depends on this frequency ratio omega 2 by omega 1. Okay? Yeah. Can I? Sure.
So these are two uncoupled pendulums or oscillators.
Two uncoupled oscillators.
Conservative.
Yes, conservative.
So both of them should form closed orbits over sufficient time.
Not necessarily, because I'm now looking at the joint motion. Wait. Okay. So if I take phi 1, this phi 1 dot is equal to omega. So phi 1 is just omega t plus phi 1 naught. All right? And the second one will be phi 2 is equal to omega 2t plus phi 2 naught. Now, if I look at when I cut through 4 dimensions, conservative system, I can have any two coordinates that I want. If I look at the phi 1, phi 2 plane, right, I can use these two what shall I do? I want phi 2 as a function of phi 1. So from the first equation, I get phi 1 minus phi 1 naught. Let me take that to be 0. Let me start at 0 there. So phi 1 divided by omega 1 is equal to t, right? And therefore, phi 2 is just equal to omega 2 by omega 1 times phi 1 plus phi 2 naught. Okay, so this is what I'm calling. Okay, so now this is obviously the equation for a straight line. So because I started with phi 1 naught over here, so that's that's where I'm going. Now these are oscillators, so these are all going to be periodic, right? So after this point, I come here. Unfortunately, it looks like I'm going to close, but I don't act, in a sleight of hand. Whether I come back here or not will depend on.
It's a Hamiltonian system, so orbits cannot cross.
Right.
So eventually,
even non-Hamiltonian systems, orbits cannot or should not cross.
I mean, a conservative system. I mean.
Yeah.
So eventually, it should form a closed orbit over Poincare.
Not necessarily, because it depends on the slope.
So Poincare recurrence and all won't apply here?
Of course it applies. Poincare recurrence is very strong, right? No, see, the point is that it will, for it to come back, you see, you would like phi 1 is equal to should be equal to 0. We started at phi 1 is equal to, okay, the initial condition was 0 phi 2 naught, right? And I want to know when am I going to come back to exactly the same point. And just work it out. It will, if omega 1 by omega, if this ratio is an irrational number, I never come back.
No.
Yeah. Hi.
Maybe the confusion is maybe like full phase space phi 1, phi 2, p1, p2, it can't close, it can't cross, right?
Yeah.
But in here, of course, it can cross. I mean, like because it's a reduced space. I mean, like in the full phase space, it wouldn't cross.
No, true. But if I just look at how these don't cross in the sense of actual crossing. One second, let me just take that to go over there. It goes over here,
Right, yeah,
and
it
then
won't cross anywhere. Right, yeah.
It goes like so.
But no, his question about crossing, I'm saying like that.
Yeah, the crossing will not happen in the full phase space. It could happen in a projection down. Okay, but. Okay, so at least it gave me a chance to now figure out, see, this is an important ratio, omega 2 by omega 1. Okay, rather than omega 2 or omega, these two could be independently irrational, but their ratio, if it is a rational or an irrational number, this is what plays a role. Because if this is a rational number, you can figure out some time when both the coordinates will be the same. Okay? All right. The joint motion of this, all right, can now be represented, actually, the Poincare section, if you like, is just an image of these intersections. See, each time the orbit comes and hits this point is a new point on the Poincare section, all right? And because this is actually a circle, all right? Those two are identified. These are all modulo 1 or modulo 2 pi or something like that, right? So here we have these points that are just going around on the circle because it is just, that is the Poincare section. All right. So, yeah. So this leads us to the study of a circle map. Okay, actually this is a trivial circle map, it's just the rigid rotation of the circle. So I've got a circle, I've got a point on it, and each time I will, each time I hit that line again, all I'm doing is to shift by a certain amount, which is this ratio omega 2 by omega 1. Right? So it's a rigid rotation. Now you think of just taking the circle and rotating it by a certain fixed ratio, and that over there is a very simple dynamical system. Theta goes to theta plus omega 2 by omega 1. Now, if you had a rational number, then what you find is that you have these evenly spaced points, okay, and it just keeps repeating. You start at some particular point, after a while you come back to that same point, and then you just keep on going, right? So here I took something like 3 by 7 or 5 by 7 or some number like that, and you find that there are exactly 7 intersections. I'm sorry that it is small. I think you can see where the actual intersections are. Right? On the other hand, if this ratio omega 2 by omega 1 is irrational, then you have the case that it can never ever repeat itself on the circle. You're rotating by an irrational fraction. Right? And okay, so this is the situation of two uncoupled oscillators. Right? For two uncoupled oscillators, I just point out to you that most often what you will find is irrational covering of the circle, because irrationals outnumber the rationals so massively. Right? The rationals have measure 0. So almost every ratio that you will find omega 2 by omega 1 is going to be an irrational number. Okay? When you couple the oscillators, and the way in which we will couple them in the Hamiltonian format or in the pendulum case will be slightly different. I'll come to that at some point in time. But when you couple these oscillators, these give rise to a family of what are called circle maps. And these have been studied extensively by people in dynamical systems. All right? And a good model for the coupling between the systems is sort of mimicked by this kind of, I mean, this is now like a canonical, this is the hydrogen atom of circle maps. All right? So K is the coupling constant. The coupling actually, the two of them are, you see this theta variable is a difference variable. It's not the actual phases of the two systems. This is related to the phase difference, if you like, of the two systems. So the circle map is, as we saw over here, right? I mean, the phi 2 and phi 1, so the differences come up over there. All right, anyway. So the point is that this circle map is theta n plus 1 is equal to theta n plus this ratio omega minus coupling times, these are all taken modulo 2 pi, sine of 2 pi theta n. Yeah? Okay. Now this has been actually studied very extensively, and it relates to the cases, I mean, it relates to the swing, it relates to coupled Huygens, all these various systems. Mainly that coupled oscillators can entrain over a wide range of frequency. Right. Now what this shows, oops. Okay. I don't know which way to explain it. Okay, so this capital omega is the ratio of the two frequencies, omega 1 is to omega 2, all right? At every rational fraction between 0 and 1, you have periodic orbits. At every irrational point, you have these orbits that never close on themselves, they are quasi-periodic. Okay, they never close on themselves, but, right. Okay. Now you can ask, what is, you can ask what is the winding number? The winding number of the system is basically the large n limit of the difference between the initial point and the final point. That is to say, how far have you wound across this joint system? When you're not, you see, if k is equal to 0, then the winding number is just capital omega. When k is equal to 0, you just wind by that number omega. Yeah? But when k is not 0, it turns out that for omega 1 by omega, for omega very close to, let us say, 1/2, for omega equals 1/2, the winding number is a half at k is equal to 0. But if k is not 0, even for small departures from omega is equal to 1/2, as the system goes, develops dynamically, eventually the frequency will become exactly a half. Yeah?
Is that because theta is going to some fixed point?
No. See, what this winding number, which in my figure is just the winding number, this is just the limit of n going to infinity of theta n plus 1 minus theta naught divided by the thetas are not defined modulo 2 pi. It's just I want to know on each cycle how much has it increased. In one case, it will go to a fixed point, but not in other cases, right? So there is homework and tutorials, right? Okay. Homework for today would be to code that up and just look at it, all right? What I want to do is to vary omega and vary k. Okay, what happens, let's say that I look at omega near a half, and let me increase k as I go up, all right? At k equals 0, no coupling, the winding number is a half, just by definition. What was shown by Arnold in a beautiful paper on Matthew equations, on the Matthew equation, but this is a common phenomenon that you see everywhere, is that as you increase the coupling, right, you have this entrainment. So omega 1 by omega 2, a little less than a half, also becomes, as time goes to infinity, and the shape of this is, okay, so in this entire region over here, you will find that the winding number is a half. That's why, because of the coupling, the way in which the coupling, etc. goes, that is why in the swing it doesn't matter if you're not exactly a half. Because you have this Arnold tongue, which actually increases outwards. So for a larger range of a larger range of omega 1 by omega 2 will all entrain onto 1/2.
So the way you have defined the winding number, if there's some constant value, it's a half or something, that means theta n is increasing at a uniform rate at large.
Absolutely, asymptotically, yeah.
Right. Okay. So then, if I take this recurrence relation, the increase of theta over one step is just omega minus k by 2 pi times that factor.
You're playing with two limits over here. If you look at the actual thetas, they will asymptotically start, going almost periodically, right? Well, I did, in preparation for the lectures, I did this. So here is the image of the winding number as a function of omega for k equals 1. Okay, k is equal to 1 is important because in this system it is known that the tongues do not touch each other until they don't even touch at k equals 1. So for every rational number, the tongue has, see, this is the tongue for a half. This is the tongue for 0, that's the tongue for 1. Then you have 1/3, 2/3. This picture is symmetric. It's known as the devil's staircase because there are an infinite number of steps from here to there. So you never, I mean, if you're going to take a step at a time, you're never going to reach the top, etc., etc. Okay? But what's also interesting is that these tongues always have this very characteristic shape. They go down and they hit this line at every rational value. All right? And the shape of these tongues is as so. This is the zero tongue, or 1:1. No, 0:1, 1:1, this is 1:2, etc., etc. At the line k equals 1, none of the tongues have overlapped, but what has happened is that each of the rationals now occupies a horizontal space, so the role of rationals and irrationals is completely inverted. And the non-phase locked states on that line is known to have fractal dimension of 0.8, which is also something you can measure in an experiment. All right? So, I mean, this is sort of, it's a classic paper of Jensen, Bach, and Bohr from the 1980s. Okay, beautiful paper, but the point over here is, and it's, you know, really catalyzed a lot of work in this, but the point is that oscillators of different frequencies, they show a certain, so you can imagine now if I have an ensemble of circle maps, all coupled with one another, they will all entrain, depending on the coupling, they can entrain onto very specific asymptotic states. Okay? And this will depend both on the initial ratios of omega as well as on the level of coupling. Beyond k equals 1, these tongues continue, and at some point they start overlapping. And when they overlap is when you have chaos. Okay, so, but the phenomenon that I'm just alluding to, this phase locking, is a non-chaotic phenomenon. It just happens because the frequencies are they're very close to rational fractions, all right? And how close do they have to be in order to catch that particular rational fraction depends on the size of the numerator and the denominator. From here you can see that the largest ones are 1/1, 0/1. Those are the ratios there. But closer to this, 1/2 is much larger than 1/3, which is larger than 1/4, which is larger than 1/5. So the denominator plays a major role in how the width of this line over here. Okay, there's all sorts of very nice scaling, fractals, etc., in this business.
So it's only certain rational fractions?
No, all of them. It's just, the other ones are just very, very narrow, because it depends on the denominator. Right? Okay, so, yeah.
In the non-term region, it's 0, or the winding number is 0, or it's
Big one?
the winding number vanishes, or it's some finite value in the non-term?
In the non-tongue, they are quasi-periodic.
So it's, okay. So it's
Yeah, the winding number is just, these are all quasi-periodic over here.
So that limit does not exist?
Which one?
The limit is not.
Yeah, I mean, see, computationally, you just don't see them, right? I mean, you don't see, okay, you identify the rational ones by the flat portions. Anything which is not flat, now if I blow this up, I'm going to have again flat. I mean, it's just, the whole picture is a fractal. So it depends on the level of, you're never going to climb all the way to the top. So the picture is of having, Maxwell's demon up there, you're up here, you're trying very hard to get to the spot. No, Abhishek, you'll find some number for the, for at any point of omega, obviously. You'll find some limit. The question is, do you find plateau or not. For every rational value, there is a flat portion.
I was trying to relate to the swing problem. In swing problem, if you are outside those terms, then you don't grow.
You don't do well.
So I would imagine that corresponds to you don't wind around, but
It's not that, because every irrational number is close enough to a rational number. So it's just that what distinguishes the phase locking is that there is a width over which you lock. The width of that locking zone, that depends on the denominator. It goes down as 1 over the denominator to some power or the other. Yeah? Okay. So, so the idea, so what I want to just discuss with you today is that why did Huygens see what he saw? And what can we say about these various states? Okay, so obviously this is a simple enough classical system. Right? I will invite you to play with the circle map subsequently, right? And we can play with circle maps, coupled circle maps, and so on and so forth. But we see these as a metaphor for collective behavior. This is only for 2 oscillators, but one can clearly, of course, couple n of them and look at them, right? And people have. And it's well known that there are phase transitions in such systems and so on and so forth. Okay. Anyway, all right. So the Huygens experiment is mimicked, let us say, by this, where you've got a horizontal beam of mass capital M, which is allowed to just slide. Okay, so you've got some coordinate x sliding in one dimension, and the 2 pendula themselves are oscillating in the same, in this plane in which this thing is sliding, and the 2 phase variables are phi 1 and phi 2. All right. Okay, so one can write down the Lagrangian if you like, as just, here is the motion of the entire thing. So the platform plus the 2 pendula, that corresponds to that one over there. This is just the equation of motion of the 2 pendula over here, just the ml squared phi 1 dot and cosine theta there, right? Here is the kinetic energy of, okay, we will not bother about this term, we just take k equals 0 finally. It's not as if the whole system is not confined in a potential. If it were, then you would put something over there, if you like. Right. Now, this is a non-inertial frame. So you will have to couple the x dot to the individual pendula, and that is the term that arises from the coupling of the pendulums to the motion of the system, and this gives rise to the following equations of motion. For the 2 pendula, phi double dot of k, there is a damping term. Okay, this damping term will come out of all this, all right? And you'll get a 1 over L and so on. This term comes out of the energy being supplied to the system. This F of k is just the force that has been put in, okay? And the equation of motion for the bar itself has got this equation for the acceleration, the damping. This, as I told you, is not going to be important, and here you've got all the pendula coupled, right? And okay, all right. So that's what I had over there. 1 second. Let me just come back to that. Okay. So what Huygens saw was that it almost always went into the anti-phase state. All right? And in the anti-phase state, let me remind you, phi 1 is equal to minus of phi 2, right? If phi 1 is equal to phi 2, then we are in the in-phase state, and in phi 1 is equal to minus phi 2, we are in the anti-phase state. So let me just use the board. Okay. So keeping that in mind, I just want to change variables to become dimensionless. I have y is just x divided by the length scale over there. Tau just becomes t times square root of g over L. This is making things dimensionless. This gives me phi k double prime plus 2 gamma times phi k prime plus sine phi k. That's equal to minus y double prime cosine phi k plus this forcing term. Okay? So basically, I've just gone from the variable capital X to capital Y, and the double dot to the double prime. Okay? Okay. And there's a similar equation for y double prime plus 2 gamma times y prime plus omega squared y is equal to minus mu of sine phi 1 plus sine phi 2 whole thing double prime. All right? And this sort of the obvious, you can figure out what is this gamma in terms of b and so on and so forth. Okay? These have to do with just the friction that is experienced by the pendulum and so on. Point is that if I now look at the variables, delta is equal to phi 1 minus phi 2, and sigma is equal to phi 1 plus phi 2, right? What I'd like to show, and I will, is that asymptotically, if delta asymptotically goes to 0, right, then the only thing that is, then that corresponds to phi 1 equals phi 2. That is the in-phase state. On the other hand, if sigma goes to 0, I've got phi 1 minus phi 2. Okay, so basically this is the idea as to why Huygens saw what he did, or why are you likely to observe synchronization, is that these two variables must show some kind of asymptotic behavior. All right. Yeah? F is the energy source that is being supplied to the system.
No, like in that pendulum experiment, it's just that initial thing, right? Because it's not continuously being pumped, right?
The actual clocks are being pumped.
Okay.
All right?
Okay.
So there is some form that is eventually chosen for F. Right now, I'm just going to put it equal to 0.
I mean, like even if I have a too simple pendulum with some flexible bar, I'll still see probably. Or
what you will probably see is that everything comes to a grinding halt. Right? Because you don't have.
No, if the air is not there.
If the air is not there, but we don't do experiments in that situation. Meaning, see, Mr. Huygens was both very inventive and also very lucky. Right? He was very lucky because the way in which he was working, it was not the overdamped limit. It would have all just come to a crashing halt. It was also sufficiently weak, but not too weak, because if the coupling was 0, then the two systems would never have synchronized. All right? And it was a very special kind of a construction that I was thinking, well, let me just, finally just two more equations. So based on, see, this is a set of two equations over here and one equation over here. K is 1 and 2. So obviously I can rewrite this to get one equation, delta double prime plus 2 gamma delta prime plus delta is equal to 0, and sigma double prime plus 2 gamma sigma prime plus sigma is equal to minus 2 y double prime. The third equation stays essentially the same. I can rewrite this as approximately phi 1 plus phi 2 for small amplitude vibrations. So this just becomes sigma double prime. Yeah? Okay. So I'm just looking at a certain limit. I want to just discuss the physics of this. See, x, the motion of the whole platform, if both of them are oscillating in the same direction, they don't feel the motion. I mean, they're in the same frame as the platform moves around. So the variable x or y is not coupled to delta, which is phi 1 minus phi 2. Phi 1 minus phi 2 going to 0, as we just discussed, was phi 1 equals phi 2. Delta going to 0 was phi 1 equals phi 2. So both of them are going together. And if the platform is moving, it just wipes out. And that's why this equation doesn't have y. Yeah? This equation, on the other hand, is coupled to the motion of the platform, because it has this y double prime. Now, even if you went to the zero friction limit, that is, if there was no friction, no air, this equation is just the equation of a simple oscillator. So this is never going to go to 0. This is just going to oscillate somewhere. This, on the other hand, will always have the coupling over here, and this will effectively, it will bring you down. I mean, there will be damping because of the motion of your beam, right? So eventually what will happen is that sigma will go to 0, i.e. phi 1 will be equal to minus phi 2. Okay? So in the majority of cases, with or without damping, right, what tends to happen is that your system just goes to the anti-phase state, because the variable sigma will go to 0, but delta will never go to 0.
The damping came from the coupling to the platform.
It comes from two sources. One is the natural friction, that is, what is B or B, capital B. Those are the natural frictions of air resistance. There is a phenomenological damping that comes because of this coupling to the other term. Okay? All right. Okay, so in a sense, this was just a lucky, the experiment itself, etc., was quite lucky, and what Huygens saw was largely because, with or without damping, it is the state of sigma equals 0 that is asymptotically reached. Okay.
What is different for the metronomes?
There, this is the other state which is important. Okay, what I'm going to do is I'm going to do the metronomes tomorrow. Okay, right? Because there's only so much one can take of ancient classical mechanics. But no, see, the point over here is that when many such systems are coupled, new kinds of states emerge, right? And one can come to that tomorrow. What I'd like, I mean, I presume almost all of you will be quite familiar with coding simple maps like so, all right? So I would just urge you to take that circle map and see for yourself these. Okay, I mean, I've given you everything that you need. That's the definition of the winding number. All right, you've got the form of the map itself. Just go ahead and look at it, and you see the for extra points, you can calculate the fractal dimension at k equals 1. The fractional dimension of the parts not occupied by the plateaus. Yeah?
So you don't get chaos in this?
Oh, there's no chaos at all. I mean, okay, so the point of today and tomorrow was basically to introduce the phenomenon of synchrony, and tomorrow I'll discuss the Kuromoto model, which is just this very nice connection between StatMech and dynamical systems, right? But the origin of the Kuromoto model, it's usually considered to be, fireflies or biological systems. We'll start with the metronomes and go from there. Yeah? Okay. Yeah?
In the previous slide, these tongues that you showed us, the shape of the tongues themselves and the dimension of the part or of it, does that depend on the form of the coupling at all?
Just 1 second. The shape of the yeah.
And the fractional dimension, I suppose, would not, but the shape of the tongues, does it depend on the coupling? And
Yeah, it would depend on the coupling. So instead of a sine function, if you took some cubic or some sort of bizarre function over there, it would.
The dimension that you're talking about?
The dimension should become, these all become universal at some point in time. Yeah. Yeah. See, the motion of both these pendulums is going together. So in some frame, you can just remove the motion of the. In a sense, they're equally affected by x. Right? Whatever the motion of x is, they're equally affected by it. So it just wipes out. I mean, I'm just doing sort of zeroth order analysis. I'm ignoring everything of quadratics and so on and so forth. Yeah.
So if I give some other type of vibration towards the base,
Yeah.
will it affect the synchronization?
Oh, absolutely. And that forms a very, for granular materials, people are forever vibrating the base and seeing the motion of oscillating particles and so on and so forth. So, yes, that is, I've only assumed that the base moves in X. I can make the base move in Y as well.
It can have some other vibrations also, like some other patterns of movement.
Not only that, if you vibrate the pendulums strong enough, people know what happens. If I take a simple pendulum and I oscillate its base of, take a pendulum and oscillate the point of suspension, Physics 101, what happens? It starts oscillating a little, but any idea? Let me repeat the question for those who are temporarily elsewhere. You've got the point of suspension, and I'm oscillating this suspension at some frequency omega, unrelated to the frequency of the pendulum. What happens? It can induce a loss of energy. What else? It goes to a resonance state. I mean, just wondering if you all have been introduced to this rather interesting phenomenon. See, when I have a pendulum, for example, this, okay? So here is my pendulum, and I'm oscillating it like so. And then all right? I oscillated vertically. If I oscillated fast enough vertically, any idea? Huh? No, it does something even more interesting. If I oscillate the point of suspension fast enough, it will just invert and it will start oscillating about. You see, this is a stable fixed point. This is an unstable fixed point. If I oscillate this fast enough, it's a parametric problem. This stable fixed point will become unstable, and the unstable one, we won't see it in that. And the unstable one goes, this one becomes stable as it goes up. You can do a beautiful experiment with a pendulum attached to a loudspeaker. The loudspeaker, and you play some heavy metal, right? It goes fast enough, and then boom, you'll see the pendulum just rising and oscillating at the top. That happens. Okay, I've seen it with my own eyes. And if you don't believe that, go and look at Arnold, Mathematical Methods of Classical Mechanics, page 160 or thereabouts. You'll find it. Or Kapitsa, or I mean, many of these other clever, but it's something that one should think about, right? So there are interesting collective phenomena that happen because you're coupling together many oscillating systems, right? And tomorrow we'll look at the metronomes because they are inverted pendula, and their equations, it will turn out sort of reduced to the Kuramoto model. Huh? I know, there is the, but I was conscious of the. Yeah, I know. I may